Y creo que es importante mencionar que, si bien afortunadamente quienes estamos aquí estamos bien, tanto familiares y amigos nuestros o de colegas nuestros, sobre todo en Cali, en el eje cafetero, en el Chocó, están afectados de maneras muy dramáticas en algunos casos. En algunos casos, la línea, en el caso mío personal, la línea es un grafo en dos pasos, gente muy dramáticamente afectada. La madre de un estudiante de doctorado mío es armenia y su casa es inhabitable en ese momento. Y esos son los casos, digamos, en los cuales no hay pérdidas de vidas humanas o gente que está mal. Entonces es importante, yo creo, en este momento, a pesar de tantos motivos tan positivos que nos han congregado y que se han visto en estos días hasta hoy, creo que es importante pensar en ellos, pensar en toda la gente que está afectada y además saber, tal vez es lo más importante, que en cada etapa hay apoyos distintos. Primera etapa, de las primeras 72 horas, bueno, 96 horas, algo así, que era el dramatismo inmediato de ese momento, que requería acciones muy ágiles, pues eso ya está pasando en este momento. Es posible que encuentre todavía personas vivas, pero ya esa etapa está pasando. Pero ahora viene toda la etapa complicadísima de reconstrucción y de toda la burocracia que hay detrás y de todo lo que sigue. De modo que hay muchas maneras de seguir apoyando eso. Aquí en la universidad hay muchas maneras de canalizar ese apoyo. Nos llegan de distintas maneras. Entonces, simplemente una invitación, no estoy diciendo nada nuevo, porque yo sé, me consta en algunos casos que conozco, muchas personas aquí han estado, de hecho, apoyando de distintas maneras, pero es importante hacerlo. Y empezamos entonces con un minuto de silencio para pensar y conectarnos un poco con eso que está pasando en ese momento, antes de presentar a Mauro. Bueno, y ahora sí, entonces continuamos con la primera parte de la sesión de la mañana hoy. Para mí es realmente un orgullo y con mucho gusto. Iniciamos con una charla de Mauro Artigiani, no aparece su nombre aquí, es Mauro Artigiani, de la casa también en este momento. Tiene un recorrido interesante que resumo muy brevemente. Su pregrado universitario en Sapienza en Roma, luego su doctorado, bueno, y maestría en la Sapienza, su doctorado en Bristol, trabaja en temas que incluyen sistemas dinámicos, geometría, como verán brevemente. Luego, varias posiciones postdoctorales, entre esas en Pisa, en la Universidad de los Andes, luego profesor de la Universidad del Rosario, y ahora presentamos nuestro tanto con mucho gusto. Adelante, luego avance.
Gracias. Bueno, eh, entonces la idea es hacer una charla un poco introductiva del área. Si alcanzo, al final tengo algún resultado más reciente. Los que estuvieron acá escucharon esto, pero pues si no llego no importa, digamos. Lo que yo quería contar un poco es una historia digamos, de mi área, que es superficie de traslación, que ahora voy a definir más o menos qué son. Pero la idea que yo quiero enfatizar un poco es que fue un poco la razón de por qué yo me enamoré de esa área cuando estaba haciendo mi maestría, y es que superficies de relación son como, pues, son un lugar donde muchas cosas confluyen. No sé, si han leído esa lecture de Manford donde dice que hay varias cosas como de síntesis muy unida de superficies de Riemann compactas, curvas radiodraicas, extensiones de cuerpos trascendentales de grado 1. Y a ese triada habría que añadirle superficies de traslación. Entonces, en un segundo te cuento por qué. Pero la idea es como ir alternando entre geometría dinámica adelante y atrás. El pointer siempre está perdido. ¿Qué logro? Suspense. No, seguramente yo creo que funciona. Pero bueno, no sé, eso, más o menos. Ok, empezamos con un poco de motivación, digamos, de una de las posibles motivaciones que es surge dinámica. La idea es que queremos jugar una versión idealizada del juego del billar. Aquí tengo una trayectoria, arranca de aquí y sigue adelante. Y como esto es una charla de matemáticas, vamos a jugar una versión idealizada. Entonces, mi pelota va a ser un punto que no tiene masa, no tiene dimensión, entonces no tiene spin, porque no es un punto, y no tiene fricción. Entonces, una vez que yo lanzo la bola, eso sigue adelante por infinito. Y las colisiones son perfectamente elásticas, es decir, que se preserva la energía, la velocidad. Y además, la ley de reflexión es la ley óptica, que no funciona para el billar de la vida verdadera. Es decir, que el ángulo de incidencia es exactamente igual al ángulo de reflexión. No me acuerdo si en la vida verdadera es un poco mayor o un poco menor, pero algo de ese estilo también es. Sí, también es spin, pero bueno, ya es más difícil. Yo soy muy malo jugando billar, entonces no puedo hacer spin. De hecho, contrariamente al juego del billar, nosotros no queremos ir a la esquina, porque si vamos a la esquina, pues no sé cómo seguir. Entonces, no vamos, eso no va a ser útil para jugar billar. Ahora, ¿cómo ven en esta figura? Pues la trayectoria es complicada. Esta trayectoria es periódica. No creo que se vean algo si no saben. Pero una cosa que sí notan es que como esto es un cuadrado, la pelota solo viaja en 4 posibles direcciones. Pero como esta trayectoria es complicada, pues queremos simplificarla. Y el precio que vamos a pagar es que vamos a complicar un poquito la superficie. Okay. Pero vamos a hacer el siguiente experimento mental, que en inglés se llama unfolding, en español creo que es desdoblamiento. La idea es la siguiente, pues nosotros cuando la pelota choca contra una pared, pues tenemos que reflejar la trayectoria, ¿cierto? Pero podríamos imaginar, en lugar de reflejar la trayectoria, de reflejar la mesa. Entonces, si reflejamos la mesa, por ejemplo, al comienzo esta trayectoria verde, pues choca entre esta pared, entonces de aquí obtengo otra copia del cuadrado, pero esta copia, pues este lado de aquí, pues está identificado con esto, por esto up está escrito aquí como un espejo. Y ahora esta trayectoria de aquí salta a esta mesa, pero la magia es que ahora sigue la misma dirección, porque pues es reflexión, es reflejado. Pero como este es un cuadrado, pues tengo solo 4 direcciones, entonces me sirven 4 copias del cuadrado. Entonces, estas 4 son exactamente las 4 direcciones que tenía antes. Es un pedacito más corto de la trayectoria, como antes, ¿cierto? Y otra vez, estos 4 cuadrados, pues no son aislados. Este lado es como este lado aquí es como este lado acá, y etcétera. ¿Sí? A ver, lo tengo. Ah, no, eso no funciona. Entonces, lo que obtengo, bueno, si sigo las identificaciones, pues este 4 cuadrado me da un toro, ¿sí? Me da la superficie de una lona. Lo tengo aquí. Una cosa que va a ser importante más adelante es que yo aquí solo necesito 4 copias, en general no necesito un número finito de copias, básicamente porque el grupo diedral generado por la reflexión de los lados es finito. Si no saben qué significa esto, más fácilmente, todos los ángulos son racionales, es decir, son múltiplos racionales de pi, escritos en adelante. ¿No? En este caso son todos iguales, pero no importa. Entonces, si yo sigo las identificaciones, básicamente esta mesa se convierte en este toro más grande. Este es como un Pac-Man, ¿no? Es como jugar Pac-Man o pues Snake, si prefieren. Cuando salgo de aquí, pues vuelvo a entrar acá, etc. ¿Sí? Entonces, esta trayectoria de pillar aquí, que aquí era complicada porque tenía otra intersección y cambiaba de dirección, ahora se ha vuelto una trayectoria sobre en esta mesa, pues en esta superficie, que es más fácil porque pues siempre va en la misma dirección y no se autointerseca a menos de que no sea periódico, que pues sigue siempre en la misma dirección. Ahora, en este caso, pues yo arrancaba con un toro y termino con un toro. Entonces, pues no he complicado mucho la superficie, simplemente es de área más grande. Pero este es un caso, pero este es el ejemplo más fácil de dibujar. Pero la cosa que es importante es que esto es un toro, yo lo estoy identificando por traslaciones, entonces pues sigue siendo algo plano, como es plano. Y entonces he convertido mi problema inicial de estudiar dinámica en esto a estudiar la dinámica del flujo geodésico en esta cosa. Y geodésica significa la línea que minimiza la distancia localmente. Pero en para manejarlo va a ser algo muy fácil, porque van todas en líneas rectas, entonces no hay ninguna, digamos, usualmente uno tiene que resolver una ecuación diferencial, etc. Pero aquí pues son líneas rectas, no es toda la vida. Entonces la idea es, como esto me permite estudiar trayectorias acá, vamos a generalizar este tipo de construcción para definir la clase de superficie que nos interesa. ¿Ok? ¿Está bien? Ok, entonces vamos a definir qué es una superficie de la superficie. Entonces, usualmente hay tres definiciones equivalentes. Yo no le voy a dar tres porque no tengo tiempo, pero le voy a dar dos. La primera con todos los detalles y la segunda, pues con menos detalles, y me lo puedes preguntar sobre el café. Entonces, La primera es una definición de geometría euclidiana, muy concreta. ¿Ok? Entonces, una superficie de traslación, S, es una colección de polígonos, a lo sumo contable, donde cada polígono está embebido en R2, que para mí va a ser lo mismo que C. ¿Ok? Entonces, esta colección de polígonos embebidos en el plano, es decir, no los puedo rotar, están ahí fijados, encajados. Tiene también una identificación en los lados, donde cada lado tiene un compañero y está identificado solo con ese compañero. Las identificaciones son hechas con traslaciones, es decir, que los dos lados tienen que ser del mismo tamaño y paralelos. Y después hay una condición un poco más técnica que dice que cuando dos lados son identificados, tienen que ser orientados de la manera opuesta. ¿Ok? Esto sirve porque yo quiero superficies orientadas. Entonces, la superficie es simplemente la unión de todos esos polígonos, módulo de identificaciones, digamos, haciendo esos pelos. Si saben la metodología, esto es muy claro, pero si no, pues tal vez hagamos un dibujo. Estos son tres ejemplos de superficie de traslación. Aquí y en todos los dibujos que voy a hacer, a menos de que no diga de otra manera, los lados opuestos son identificados. Entonces, esta ficha de Tetris, este lado está identificado con esto con esto, esto con esto y esto con esto. ¿Sí? Y pues justamente esta es paralela a esto, del mismo tamaño, y esto está orientado, digamos, hacia así. Digamos, el polígono está a la izquierda y esto está, bueno, pues no, el polígono está a la derecha, aquí está a la izquierda. O si prefieren normal, saliente, apunta en direcciones opuestas. Esto es un doble pentágono, entonces pues cada lado solo puede ser identificado con uno. Y yo siempre hago estos dos porque son bonitos, pero pasa un poco lo mismo que Federico siempre dice con los números. Es que, pues si uno le pregunta un número real, usted seguramente va a decir un entero positivo y pequeño. 3, 11, 2. Pero pues con probabilidad 0, un real es así. De hecho, un real con probabilidad 1 es trascendente. Que pues básicamente no tenemos ejemplos. Esto es lo mismo. Esto tiene probabilidad 0. Esto tiene probabilidad 0. Esto tiene probabilidad 0. Entonces le voy a dibujar una superficie genérica, que es algo como esto. Y les digo cómo se hace, porque es fácil. Usted toma un cierto número de vectores en el plano, que le gusta, y hace una línea, pues, un broken line, lo pega uno después del otro. Después elige una permutación de esos vectores y hace la misma línea en el orden permutado desde el mismo punto. Entonces si usted lo elige decentemente, le da un polígono cerrado y eso va a ser genérico. Esto es casi genérico porque tiene una involución, pero pues básicamente es genérico. ¿Okay?
Perdón, la pregunta es, tú dices, ¿quién es Pablo? ¿Quién?
Sí, pero pues aquí se ve, ¿no? Pero pues en la construcción que acabo de dar, como uno tiene pone dos veces el mismo vector, pues esa es la elección. Y aquí, pues, como digo, son los opuestos, ¿no? Entonces, digamos, esto se podría identificar con esto, pero no, pues no está escrito, entonces son los dos opuestos. ¿Ok? Ok, una cosa importante, que siempre es un poco difícil la primera vez que uno ve, es que la superficie es canónica, pero la colección de polígonos no. ¿En qué sentido? Que, pues si yo tengo una colección de polígonos, yo siempre puedo cortar a lo largo de una diagonal, y ahora divido el polígono en dos polígonos. Y la diagonal que obtengo, pues por supuesto son dos lados ahora, que son paralelos, del mismo tamaño, y uno tiene el polígono a un lado y uno tiene el polígono al otro lado. O digamos, el movimiento opuesto, si yo tengo dos lados que son identificados, los puedo pegar y ahora tengo un polígono más grande. Estos movimientos se llaman cut and paste, o cortar y pegar. Y a veces son fáciles de ver, pero a veces no son tan obvios. Digamos que si yo le hubiera dado esta especie de estrella y este doble pentágono, pues tal vez no sería obvio que es exactamente la misma superficie. Pero sí lo es, porque yo puedo cortar, digamos, las puntas de la estrella y moverlos, y esto es exactamente igual a eso. No siempre es obvio, pero es muy importante. ¿Nota? Ok. Ahora, para los que saben un poco de geometría diferencial, deberían estar un poco asustados, porque pues yo estoy haciendo identificaciones con traslaciones, que son isometrías. Entonces, si yo tengo algo en el plano, y el plano es plano, cuando hago estas identificaciones, pues debería obtener solo cuadros de géneros 1. ¿Por qué? Pues por un teorema que se llama Gauss-Bonnet, que me dice que si yo integro la curvatura, si integro 0, me da 0, y eso debería darme la característica de Euler, que es 0 solo si el género es 1. Entonces, si usted hace el cálculo de característica de Euler de esto, le da 2. Entonces, pues, o Gauss-Bonnet es falso, o yo estoy diciendo una mentira. Y como todos creemos a Gauss, yo estoy diciendo una mentira. ¿Cuál es la mentira? La mentira es que esa métrica no es plana en todo punto, pues en casi todo punto, pero no es una métrica suave. Es decir, los vértices de los polígonos son unos vértices, son puntos especiales. Por ejemplo, si usted se fija siguiendo las identificaciones, todos los vértices de estos cuadrados son el mismo punto en el cociente. Entonces significa que ese punto es un punto especial. Usualmente, si yo tomo un punto cualquiera, no sé, este punto aquí, pues una vecindad tiene un ángulo alrededor de 360 grados, como el plano. Pero este punto aquí tiene una vecindad, digamos, tengo que dar 3 vueltas para volver al punto inicial. Entonces, esto es una singularidad de tipo cónico. ¿Okay? Y lo que siempre pasa es que es una singularidad de tipo cónico de un múltiplo entero de 2 pi. ¿Okay? Entonces, son singularidades por la métrica, pero no son tan feas. Eso es lo que quiero decir. O por ejemplo, esto que es un decágono, aquí tengo dos singularidades, cada una de ángulo 4π. Esto también es de género 2. De hecho, hay una generalización de la fórmula de Gauss-Bonnet que se puede demostrar también con otras herramientas, pero pues, que me dice lo siguiente, que el número y, ¿cómo se dice? Y amplitud de la singularidad cónica, si yo tomo la suma de eso, me da menos la característica de Euler. Entonces, lo siguiente determina el género, o si prefiere, el género de las restricciones sobre el tipo de singularidades. Entonces, digamos, el género 2, o tengo esta que tiene una sola singularidad de orden 6π, o tengo dos singularidades de orden 4π. Entonces, estas familias de superficies de la estación, que tienen el mismo patrón de singularidades cónicas, los empaqueto en algo que llamamos strata. Más adelante le voy a decir la terminología, porque se llaman así. Tiene que ver con algo de geometría algebraica, pero pues por ahora no importa. Este es un elemento importante. ¿Ok? Ahora, como las identificaciones son hechas por traslaciones, que son isometrías, en el plano, las geodésicas son líneas rectas. Entonces, en el cociente, en la superficie que obtengo, también obtengo que las geodésicas son líneas rectas, pero pues hay que pensar que a veces me toca como cruzar el lado, ¿no? Bueno, no es siempre la que yo dibujaría en R2. Hay que pensar que está en el polígono. Por razones históricas, y esta es tal vez una terminología que me va a salir, una geodésica que conecta dos singularidades no necesariamente distintas se llama una conexión de silla. Eso viene de mecánica newtoniana, pero pues no tiene que saber nada de eso. De hecho, yo no sé nada de eso. Simplemente no sé. Otra cosa que no sé si alcance, pero pues podría ser relevante para... Pues no, va a ser relevante más adelante. Es que las geodésicas cerradas no vienen aisladas. Es decir, cada vez que yo tengo una geodésica cerrada, yo la puedo mover un poquito hacia a izquierda o hacia derecha y obtengo otra geodésica cerrada. Entonces, lo que pasa es que las geodésicas cerradas follan un cilindro que yo voy a agrandar hasta que en algún punto llega a una conexión de silla y ya ahí no puede seguir. Entonces, por ejemplo, en esta ficha como de Tetris tengo dos cilindros horizontales maximales y dos verticales. ¿Ok? Y esto siempre va a pasar. Digamos, sí. Esto también, un segundo lo repito, que pasa también en el coro. ¿Ok? Ok, esa es la primera definición. Si yo parara aquí, muy probablemente ustedes pensarían que todo lo que estoy diciendo es muy aburrido. Porque, pues, esta es geometría euclidiana. Sabemos todo de geometría euclidiana. Se hace en colegio, ¿no? Entonces, si espera solo esto, pues sería muy aburrido. Y no sería, digamos, no habría nada de la riqueza que yo le he prometido al comienzo. No estaría estafando. Pero no estoy estafando. Porque ahora le voy a dar otra definición que este complementa a otro mundo. Claramente es equivalente, ¿no? Una superficie de la sección es una pareja x-ómica, donde x es una superficie de Riemann y omega es una uniforme holomorfa no constantemente 0 sobre x. Si no sabes qué significa eso, una superficie de Riemann es una superficie que localmente se parece al plano complejo y hay una manera de decir cuáles son las funciones holomorfas sobre esa cosa. Bueno, una forma lo explicó Seni el lunes, entonces ya son cinturón negro de eso, no lo voy a explicar. La equivalencia no es difícil, digamos, de los polígonos a este es muy fácil, porque los polígonos están en R2, es como el plano complejo. Entonces, son un subconjunto de una superficie Riemann, son superficie Riemann. Y la uniforme es dz. Y dz está invariante por traslación, entonces desciende en el cociente. La otra implicación es un poquito más difícil, no la quiero hacer. Hay todo un diccionario entre cualquier cosa que yo le acabo de decir y la versión compleja de eso. Y la cosa importante, que yo voy a decir más adelante también, es que este hecho que existe este diccionario me permite decir, mire, yo tengo dos cajas de herramientas en principio muy diferentes, que son la geometría compleja y la geometría euclidiana. Y de hecho más adelante va a aparecer también la geometría hiperbólica. Esas dos cajas de herramientas son muy diferentes, pero están hablando del mismo objeto. Entonces, a veces es más fácil hacer la pregunta en un lenguaje y contestarla en el otro, o al revés. Y hay preguntas que son naturales en un lenguaje, pero a veces son más fáciles de resolver en otro. Entonces, esa riqueza de puntos de vista es lo que hace que hay mucha gente trabajando en esta área desde los últimos 40 años. Y pues, de eso los voy a convencer. Espero. Ahora, yo no voy a hacer todo el diccionario, pero pues le quiero decir solo un ejemplo. Entonces, yo le he dicho que tengo esas singularidades. Las singularidades, desde el punto de vista complejo, son los ceros de la uniforme holomorfa. Porque, pues, por resultados de superficie Riemann, tengo un cero de orden K. Entonces, significa que localmente puedo escribir mi uniforme como z a la K de z. Eso es como si fuera dzk más 1. Entonces, significa que localmente mi superficie Riemann es como un cubrimiento K más 1 del plano. Es decir, exactamente tengo esa singularidad de orden cónico 2K más 1 por ejemplo. Si no saben qué significa esto, pueden ignorarlo. Esto es solo para decirle que no estoy diciendo mentiras. Estoy diciendo un ejemplo de la traducción. ¿Ok?
No lo quites.
Aprovecho para tomar. ¿Preguntas? ¿Dudas? ¿Quejas?
Las superficies de traslación resultan cero, pues, porque las singularidades son como tan...
Pues uno podría, pero digamos, desde el punto de vista diferencial, son como superficies de riemannianas con una métrica singular de tipo cónico. Es como si fuera un cubo. Pero son mejor que un cubo, porque cuando usted da la vuelta a un cubo, pues la dirección, pues si usted entra en esta dirección, sale rodando de 270 grados. En esto, si yo entro así, salgo así. Pero oggi possono aparecer en
Ok.
Ok, hay una magia que pues si uno sabe, digamos, si uno pasando el tiempo haciendo matemáticas se vuelve cínico, pues la vida también lo vuelve cínico, y uno como que ya no se sorprende de los milagros. Pero hay un milagro que pasa, pues hay varios milagros en la charla, pero uno es los espacios módulos. Pues pasa este milagro en geometría algebraica y también digamos, en geometría compleja, que yo tengo un objeto geométrico, que eso naturalmente tiene ciertos parámetros que me definen una familia de estos objetos. Y lo que no debería pasar, pero pasa, es que hay un espacio geométrico que describe esos parámetros. Eso es un milagro, pero pasa. Entonces yo le voy a contar un poquito de eso. Y como es difícil definir qué es un espacio módulo, yo no lo quiero hacer. Le quiero hacer un ejemplo, que es como el ejemplo que guía, y después voy a mover mucho las manos en los otros casos. Ah, perdón. Entonces, un ejemplo muy importante de superficie de la rotación es el tono plano. Entonces, mucha parte de la teoría es como tratar de ver qué pasa para toros planos, para el toro, y ver si logramos, si algo parecido pasa para la superficie de rotación. Usualmente no exactamente, pero algo se puede hacer. Entonces, dar un toro es como dar un retículo. Un retículo significa, ustedes verán dos vectores en C que son linealmente independientes sobre R, es decir, no uno múltiplo del otro. Y después tomas combinaciones enteras. Entonces, por ejemplo, aquí tengo esto que es el retículo hexagonal. Estos vienen en un espacio de módulo. Y esto es un caso donde se puede hacer fácil. Entonces, yo puedo hacer la siguiente cosa. A menos de rotar y dilatar, yo puedo asumir que el primer vector que elegí es el vector 1, 0. Y esto quiero que sea el más corto de mi superficie. ¿Okay? Yo tomo el menor vector de mi retículo y lo normalizo para que sea el vector horizontal 1, 0. Como el conjunto es discreto, lo puedo hacer, ¿no? Y tomo lambda 2 como el segundo vector más corto que está en el retículo, que no sea linealmente dependiente con el primero. Entonces, ¿cómo tiene que ser más largo que el primero? Su norma tiene que ser por lo menos 1, pues si no sería más corto. Significa que tiene que estar afuera del círculo unitario. Y ahora, si yo tengo ese vector así, yo lo puedo mover con el vector 1, 0 y sigue estando en el retículo. Entonces significa que su parte real la puedo normalizar para que esté entre menos un medio y un medio. ¿Cierto? Porque pues si no está ahí, pues simplemente lo cambio por el vector que le añado 1, 0 muchas veces. Sí, significa que cualquier retículo se puede poner en biyección con un retículo que está en esta especie de banda, que está afuera del círculo unitario y va hasta infinito. ¿Sí? Y si usted me da un punto aquí, yo le puedo dibujar el retículo, porque el primer vector es 1, 0, y el segundo es exactamente el vector que va de 0 hasta este punto. Entonces, por ejemplo, un vector, un retículo que está muy arriba, es un retículo muy delgado. Aquí está el toro, el cuadrado, y aquí está el hexágono, el que teníamos. Ahora, entonces, pues siguiente, cada punto aquí, cada punto del interior me da un único retículo. Hay un pequeño problema, ahora es que si yo tomo este vector aquí, o el vector que está exactamente en el lado opuesto, son el mismo retículo, porque son traslados de 1, 0. Entonces yo tengo que tomar este lado y pegarlo con este lado. Y bueno, es un poquito más complicado, pero también puedo pegar este lado con este lado, porque es la rotación de 90 grados. 180.
Entiendo por qué el hexágono. Estaba esperando como dominios fundamentales que fueran paralelogramos, ¿verdad? ¿O por qué un hexágono?
La pregunta es, ¿por qué esto da un toro?
No, ¿por qué un hexágono? O sea, los dominios fundamentales de
Sí.
los retículos.
Ah, bueno, sí, bueno, sí, ok. Puedo, si quiere, puedo cortar esto y lo pego aquí y ahora me da un paralelogramo. Pero como que uno se pierde, digamos, cuando lo veo como hexágono me doy cuenta que es un punto especial, es más simétrico del usual. Si lo pongo como paralelogramo es como raro. Y lo que obtengo, esto que obtengo es una superficie. Pues es un órbito, efectivamente, porque estos dos puntos son puntos raros. Pero si no sabe que es órbito, su superficie está bien. Ok, yo quiero hacer lo mismo para superficie de traslación, pero pues eso es difícil, entonces no le voy a decir cómo se hace. Digamos, después voy a decir unas palabras que para la gente que saben significan algo, para la gente que no sabe no significan nada, pero le voy a decir cómo se hace localmente, ¿ok? Entonces yo le voy a describir una vecindad en mi espacio módulo de esta superficie, ¿sí? Entonces, esto es un polígono, los polígonos me dan una superficie. ¿Cómo hago para encontrar una superficie cercana? Pues modifico un poquito los lados. Si modifico un lado, tengo que modificar también su compañero. Entonces, esta superficie, que es básicamente esta, son muy cercanas. ¿Okay? Estas coordenadas se llaman las coordenadas de los periodos y son exactamente las mismas que nos contaba el lunes. Pero de hecho son más fáciles porque aquí tengo uno. Y bueno, voy a decir unas palabras para la gente que sabe que me vaya bien, si no, ignoren por los siguientes 30 segundos. Básicamente, uno tiene espacio módulos de curvas y las coordenadas son un elemento de la cohomología relativa a singularidades. Entonces, yo tengo un fibrado sobre eso y las coordenadas son exactamente la integración local, son los periodos. Y se llama estrada exactamente porque son como una tajada de ese fibrado vectorial.
Una pregunta, Mauro. En el ejemplo como paradigmático que pusiste, que eran los toros planos, la topología está fija. Tienes una superficie topológica de género 1, pero en estas cosas estás variando la topología.
No. Yo aquí la topología es fija porque esto tiene género 2, esto tiene género 2. Y de hecho, con estas modificaciones, esto tiene el número de singularidades y el tipo es fijo también. Si yo, por ejemplo, colapso dos singularidades, eso se escapa a infinito en mi espacio módulo. Por eso, digamos, estas son coordenadas locales del estrato, de lo que yo llamo estrato, que significa el género es fijo y el número de tipo de singularidades es fijo.
Okay.
Ok, una herramienta fundamental en toda esta área es algo que ustedes aprendieron en la neuronal, que es matriz. Entonces vamos a la matriz de 2R porque yo quiero preservar el área. ¿Okay? Entonces, por ejemplo, si yo tomo este es un polígono del plano, puedo actuar sobre el polígono con esta matriz. Y si yo tenía dos vectores que tenían el mismo tamaño y eran paralelos, después de aplicar la matriz siguen siendo paralelos y del mismo tamaño, pues probablemente diferente al anterior, pero pues siguen teniendo uno el otro, el mismo tamaño. Entonces, esa acción va a ser muy importante más adelante y ya tiene algo de dinámica. Uno puede mostrar que es una acción por homomorfismos, etcétera, pero no importa. Ahora, una cosa que tal vez no es obvia es que esta superficie es igual a esta superficie con KTP. Entonces, el estabilizador por esta acción, es decir, las matrices, cuando yo le pego a mi superficie me da la misma superficie, se llama el grupo de Ricci. Y va a ser un actor importante, lo que voy a decir más adelante. ¿Ok? Ahora, mucho de lo que uno trata de hacer es ver qué pasa en los toros y tratar de adaptarlo. Pero hay una distinción muy importante, que es lo siguiente. El espacio de módulo de los toros, que yo les dibujé, es lo que se llama un espacio homogéneo. Es decir, SL2R actúa de manera transitiva. Es decir, si usted me da dos toros distintos, hay una matriz que manda uno el otro, siempre. El espacio de la superficie de la estación no es homogéneo. Es decir, no hay ninguna matriz que me manda el doble pentágono en el octágono, aunque ambos tienen género 2 y una sola singularidad de ángulo 6π. Entonces, no obstante, más adelante le daré un ejemplo muy importante. Muchas cosas que pasan en espacios homogéneos siguen pasando en esos espacios. Pero pues la demostración suele ser mucho más complicada. Pero no imposible. Bueno, no sé. Hay unos que son imposibles. Ok. Bueno, hablamos de geometría dinámica, porque hasta este punto tal vez hay geometría, pero hay muy poca dinámica. Y pues dijeron que yo hago sistemas dinámicos, entonces pues. Entonces, en la superficie de la estación, las geodésicas son líneas rectas. Y a menos de rotación, yo puedo estar interesado solo en el flujo vertical, porque básicamente es la misma cosa. ¿Sí? El problema es que estudiar esa cosa, pues a los dinámicos nos interesa estudiar el comportamiento estadístico de esas cosas, es decir, para mucho tiempo qué va a pasar, ¿sí? El problema es que usualmente eso es muy complicado. Por ejemplo, esta es una trayectoria, no es como evidente donde empieza y donde termina que esté pasando, ¿no? Entonces, lo que uno puede hacer es que puede renormalizar. Es decir, uno puede actuar con esta matriz que está en el C2R. ¿Y esta matriz qué hace? Pues achica la dirección vertical y agranda la horizontal, ¿cierto? Entonces, yo puedo tomar esto, rotarlo de manera que esta línea se vuelve vertical, actuar por un cierto tiempo aquí y después volver a rotar. Y lo que obtengo es esta superficie que no es exactamente igual a esta, pero es muy cercana. Pero esta trayectoria que aquí era larguísima, aquí es mucho más corta. Entonces, en mucho menos tiempo pasa lo mismo. Eso, el ejemplo que yo usualmente hago es como cuando usted mira una serie televisiva y hay un episodio muy largo donde no pasa nada. ¿Y usted qué hace? Pues fast forward. Esto es exactamente lo que estamos haciendo. Yo acelero el tiempo para saltarme toda la parte aburrida y ver qué está pasando. Ok. Ahora, le voy a decir, digamos, en esta diapositiva, la próxima es lo que yo quiero que ustedes se lleven a la casa de toda mi charla. Entonces, si están durmiendo, despiértese. Entonces, tenemos dos sistemas dinámicos. Uno es el flujo en una dirección en mi superficie. Por ejemplo, esa especie de L que tenía antes y esa cosa naranjada que tenía, ¿cierto? Eso es un sistema dinámico. Después tengo la órbita bajo GT de mi superficie en el espacio de módulo. Esta es una caricatura del espacio de módulo. ¿Ok? Entonces yo tengo esta superficie aquí, con este flujo, hago le pego con esa matriz GT y obtengo esta superficie acá, aplastada por eso. Y la magia es que muchas veces estudiar uno me da información sobre el otro y al revés. Entonces la filosofía es la siguiente. Este es un método teorema, no es un teorema, es una filosofía, que dice lo siguiente, dice, sembrar en el espacio de parámetros, en el espacio de móduli, me permite cosechar en el espacio de fase o en la superficie especial. Este dibujo me lo robé de un survey de Forni Mateos, no lo hice yo. Yo soy incapaz de dibujar cualquier cosa.
¿Puede echar atrás un momento?
Puedo saltar.
Gracias.
¿Es fijo o es variable?
¿Ah?
¿Es fijo o es variable?
No, te varía, te varía.
¿Es la órbita?
Sí, esa es la orden. Sí, sí. Ese es un, digamos, ese es el, sí, es como el tiempo. Ese es un flujo geodésico, de hecho, en ese espacio módulo una cierta medida. Pero no quiero definir eso porque es complicado.
O sea que la acción de SL2, ¿estabas actuando con SL2R o con SL2Z? O sea,
Yo estoy actuando con este 2R y esto es como, este es el subgrupo diagonal que está ahí.
Pero es que mi pregunta es, en el caso de toros planares,
Sí, no, yo voy ahí, yo voy ahí. Sí, sí, sí.
la clase conforme.
En un poco de tiempo voy ahí. Ya te contesto en un par de euros.
Ah, pero ese sí es en SL2R.
Sí. Bueno, le quiero hacer, si logro hacer dos implementaciones de esa filosofía. En la segunda contesto lo que acabo de preguntarle. Otra vez, miramos qué pasa en el toro. En el toro, la dinámica es muy sencilla. Si la pendiente es racional, toda la línea es periódica. Si la pendiente es irracional, toda línea es densa y uniformemente distribuida. Esto significa que pues, es densa y además el tiempo que pasa en una región depende solo de su área, no de donde esté o de su forma. Es decir, si usted corta su toro en la mitad, asintóticamente me voy a demorar a estar más tiempo, me da tiempo en la mitad y me da tiempo en la otra. No importa cómo lo divide en la mitad. ¿Ok? La palabra técnica es únicamente el código, pero no quiero definir. ¿Ok? Ahora, esa es una información sobre una superficie específica, pero la filosofía me dice que tiene que estar reflejada por algo en el espacio de módulo. ¿Ok? Ahora, yo aquí lo hago por la vertical, que es un ejemplo especial de superficie de dirección racional, ¿no? Si yo hago GT a este toro, bueno, efectivamente estoy haciendo G menos T, pero pues será más fácil dibujarlo. Lo que hago es que esto se aplasta. Se aplasta en una dirección y se extiende en el otro. que era lo que yo estaba diciendo. Esta superficie está escapando a infinito. Su geometría está degenerando. Lo que está pasando es que hay una curva cerrada que yo estoy achicando siempre más. ¿Y qué pasa si yo hago una dirección irracional? Pues una dirección irracional, imagínense, yo tomo mi toro, lo roto un poco, lo aplasto y después lo vuelvo a rotar. Pues al revés. Lo que obtengo es que, al contrario, la geometría no degenera, vuelvo muy cercano al punto inicial y siempre me quedo en una región compacta. Pues no escapa hasta infinito. Eso es lo que pasa en el toro. Entonces, si la filosofía es correcta, debería pasar también en superficie de translación. Entonces, sumarizando, si la geometría no degenera, entonces el flujo es únicamente el gol. Y pues aquí tengo una caricatura. Esta es mi superficie inicial, que tiene dos singularidades, que tiene dos. Y les estoy mostrando un par de maneras de degenerar muy fácil. Hay cosas mucho más complicadas para pasar, pero esto es bien. Aquí estoy achicando una curva. Aquí estoy haciendo lo que me preguntaba antes Leonardo. Estoy aplastando las dos singularidades una contra la otra. Y esta es un punto muy cercano a esto. Es un poco aplastado, pero es muy parecido. Aquí la geometría no está degenerando. Entonces, el criterio de Mason me dice que si yo tengo una superficie compacta, de translación compacta, S, si cuando le pego con este GT, este es recurrente en espacio de módulo, es decir, que vuelve arbitrariamente cerca a mi punto inicial, no se escapa al infinito, entonces el flujo vertical en la superficie S es únicamente ergódico, es decir, es denso, cada trayectoria es densa y uniformemente distribuida. Entonces, esto me dice, si la geometría de la superficie no degenera cuando yo hago esto, el flujo vertical se comporta muy bien desde el punto de vista dinámico. Esa es exactamente la filosofía. De hecho, este es el momento donde nació la filosofía. ¿Vamos bien? ¿Dudas, preguntas, quejas?
O sea que el metateorema sí es un teorema, ¿no?
No, porque esa es como una implementación del metateorema, pero, digamos, mejor dicho, es un metateorema porque hay instancias donde eso funciona.
¿Qué quiere decir únicamente ergódico?
Únicamente el código significa
Que sea en metáfora.
que la definición, que cada trayectoria es densa y uniformemente distribuida. Es decir, que si usted toma un subconjunto de su superficie, el tiempo que pasa ahí depende solo del área.
Ok, de la probabilidad, ok.
Del área. Digamos, formalmente significa que la única medida invariante es la medida de Beck. Pero pues yo no quiero decir medida porque la gente, digamos, los estudiantes no saben, entonces no los quiero asustar. Ok, ahora veamos a la pregunta de Leonardo. Y mi segunda implementación, que es donde va a entrar un poquito de geometría hiperbólica. ¿Ok? Entonces, hasta el momento yo solo he usado el subgrupo diagonal de S2R. Yo he usado solo las matrices diagonales. Pero hay muchas otras matrices que no son diagonales. Pues veamos qué pasa con eso. Entonces, la idea es que cuando yo estudio toda la órbita de S2R, de mi superficie, estoy mirando como todas las posibles deformaciones afines de mi superficie. Digamos, la similitud que yo usualmente hago es como cuando usted va a un museo y ve una escultura. Usted la puede mirar de aquí, la puede mirar de acá, le puede dar la vuelta, y cada punto diferente le da una visión diferente. Siempre es la misma escultura, pero está mirando en un punto de vista diferente y sabe algo diferente. Entonces, aquí, pues, claramente, la órbita de S2Z era complicada, no lo digo de todo. Aquí está solo la parte de S2Z, las matrices enteras. Que ya es un grafo, este es fácil, es chiquitico. Los grafos crecen mucho cuando domo más cosas. Pero pues eso para mostrarle que pues, son más o menos similares, pero no son exactamente iguales. Digamos, si yo le hubiera dado esta y le hubiera preguntado, ¿está en la misma órbita de esa otra? Pues tal vez no habría sido obvio. Yo no habría sabido la respuesta si no haciendo el ejercicio. Ok, pero vamos a ver qué podemos decir sobre la órbita de S2R. Y vamos a ver primero el toro, pues siempre esto es como nuestro ejemplo, ¿no? Entonces, el toro tiene un grupo de Beach, que le recuerdo significa las matrices que estabilizan mi superficie, muy grande. Es S2Z. Ahí tengo el dibujo. S2Z está generado por estas dos matrices. Y pues ambas fijan un flujo. Ese grupo es muy grande, en el sentido que es un retículo. Esto es otro significado de la palabra retículo, son relacionados, pero significa lo siguiente, que este grupo, S2Z son básicamente elementos, son como 4 números reales, básicamente. Viven en R4. Entonces yo puedo tomar la medida, el volumen de R4. Y cuando hago este cociente, por cosas de la vida, tengo un volumen abajo y ese volumen es finito. Y nosotros estamos felices cuando el volumen es finito porque uno puede hacer teoría ergódica, que, bueno, tiene que ver con medidas todavía. ¿Ok? Entonces, ¿será que si yo tengo un grupo de Beach grande para una superficie de rotación, también puedo decir algo? Pues sí, porque si no. Eso se llama la dicotomía de Beach. La dicotomía de Beach dice lo siguiente: si yo tengo una superficie de rotación compacta, que tiene un grupo de Beach grande, es decir, que es un retículo dentro de SL2R, entonces pasa exactamente lo mismo que pasa en el toro. O cualquier trayectoria es periódica, o cualquier trayectoria es densa y uniformemente distribuida. Y además, es aún más, cuando son periódicas, yo tengo más de un cilindro. Y cada vez que yo tengo un cilindro, yo voy a hacer algo que se llama un twist de Lens, que significa tomar mi cilindro y dar la vuelta a la tapa de arriba, completa. Y yo puedo hacerlo en cada cilindro. Y Beach me dice, hay una manera de tomar un múltiplo de un twist en un cilindro, un múltiplo en el otro, de manera que los puedo pegar para un twist global. Entonces, esto me está diciendo, mire, si usted tiene muchas simetrías, eso es lo que tiene que pensar. Si su geometría es muy bonita, tiene muchas simetrías, el flujo se da cuenta de eso. Entonces, que yo en la charla decía de geometría, de dinámica, geometría y atrás. Este es el atrás. Si la geometría es bonita, tengo muchas simetrías, la dinámica es bonita. No es un sí, solo sí, pero pues. Pero pues aquí la filosofía se nota tal vez un poco menos, entonces, bueno, hay un hecho, que es un teorema de John Smiley, que me dice que el retículo, perdón, que el grupo Beach es un retículo, sí, solo sí, la órbita de mi superficie bajo S2R es cerrada en el espacio de módulo. Que es muy difícil que esto pase. Ahora sí es la filosofía. Si la órbita de S2R es cerrada en el espacio módulo, tengo muchas simetrías y el flujo pues es optimal. ¿Ok? Creo que tengo como... tengo 6 minutos, entonces puedo hacer un par de... 10 minutos. ¿Hay preguntas? ¿Cómo quiero decir otra magia? Ya después. Entonces...
Yo tengo una pregunta. En el caso del toro plano, uno puede pensar el espacio móvil como clasificando clases conformes de métricas riemannianas.
Sí.
No sé si acá uno pudiera usar el diccionario de que lo que estás haciendo es tomar métricas con singularidades cónicas y clasificándolas también conformemente. ¿Eso es equivalente al módulo space que estás haciendo?
Pues sí, porque básicamente, digamos, bueno, es una pregunta un poco larga, pero uno, digamos, como yo pienso el espacio de módulo, para mí es un cociente de Stagg-Miller. Yo soy una enfermedad diferencial. Para mí es un cociente de Stagg-Miller, entonces está haciendo exactamente eso. Yo tomo, de hecho, tomo el fibrado sobre el Stagg-Miller, que es trivial, y lo cociento por la acción del mapping cross-group. Y obtengo espacio módulo. Y, pues, si quiere, hablamos más tarde, porque ese sí es más largo. Ok, ese es muy raro. Esto pasa con probabilidad cero. Yo no me espero esto. De hecho, si usted me da una superficie genérica, lo que uno puede mostrar es que cuando yo tomo la acción de 0 de esa va a ser densa en el espacio módulo. Es decir, cuando hago el cierre, me da todo el estado. Entonces uno se podría preguntar, bueno, ¿qué pasa en general con esta acción? ¿Cuáles son las posibles órbitas? Prácticamente una clasificación es difícil, pero uno podría esperar algo. Y aquí hago, digamos, voy a decir algo. Yo le dije, estos no son espacios homogéneos, ¿no? Pero hay unos teoremas bellísimos, que son demasiado lindos para ser ciertos, pero son ciertos. Son los temas de Marina Rafner, de final de los 80. ¿Qué me dicen? Si usted tiene un grupo de Lie y tiene un retículo dentro del grupo de Lie, como el C2R representado de C2Z, por ejemplo, y actúa sobre esto con matrices unipotentes, como las que son triangulares superiores, por ejemplo, y actúa sobre los puntos y toma el cierre, eso si lo hace con un sistema dinámico general, eso es feo. Usted toma un sistema dinámico general, toma un punto, la órbita y el cierre, eso usualmente da un fractal asqueroso que no tiene la menor idea de qué ser. Y Ratner le dice, en los grupos de Lie pasa una magia, y el cierre de la órbita es como si usted tomara un subgrupo más grande de su matriz y actuara con eso. Es decir, su órbita es homogénea, el cierre de su órbita es homogéneo. Y es básicamente como un subespacio de lo que tenía antes. Ahora, esto pasa en los ejemplos extremos, pues, porque en este caso la órbita ya es cerrada, es homogénea, porque es exactamente la órbita, es homogénea. Y cuando es todo el estrada, pues bueno, no es homogénea, pero pues se porta bien. Entonces uno se podría preguntar si esto pasa también para otras órbitas. Entonces, aunque si los estados no son homogéneos, hay un milagro, que es un teorema de Esquim y de Nomani. Es un teorema de 250 páginas, ¿no? Eso. Y usa de manera no trivial resultados muy complicados de teoría de probabilidad. ¿Qué dice lo siguiente? Si yo tomo una superficie cualquiera, toma su SL2R órbita y toma el cierre en el espacio de módulo. Esto, que a priori podría ser una cosa asquerosa, en las coordenadas locales es una variedad fina. Es decir, hay un número finito de ecuaciones lineales que me describen mi espacio. Eso es un milagro. No hay ninguna otra manera de escribirlo. Y tengo que decir, esto es cierto para SL2R, pero si usted lo trata de hacer con la matriz triangular superior, es falso. Es dramáticamente falso. Hay varios artículos de John Shaika, John Smiley y Barak Weiss donde muestra que es falso en cualquier manera. Hay cosas que viven en una cosa y acumulan afuera de su espacio, pasan mucho tiempo cerca de algo, pero no acumulan ahí. Como que cualquier cosa que se puede pensar que va mal, va mal. Además, pasa otro milagro, es que estos son variedades afines en estas coordenadas. Pero este espacio es una variedad algebraica. ¿Qué cosa es social? Y Philip me dice, estos son también variedades algebraicas. Esto es un milagro. Yo espero lograr, digamos, decirles. Bueno, solo para cerrar, pues yo justamente no voy a decirle lo del conteo, no me importa. Pero pues quiero repetir lo que estaba diciendo. Quiero hacer como un wrap up. Entonces, yo empecé la charla hablando de dinámica dentro de un polígono. Y esa dinámica me ha llevado a hablar de superficies de la estación y geometría de superficies de la estación. La geometría de las superficies, como te generabas o no su geometría, las simetrías que tenían, me ha ayudado a estudiar la dinámica. ¿Y cuál es el puente entre estos dos mundos? Pues el puente es la acción de C2R, que está detectando las simetrías y también cómo degeneran bajo ese flujo. Entonces, la magia que pasa en superficie de la estación es que la geometría de la dinámica no es que exactamente una determine la otra, pero van muy, muy de la mano. Y muchas veces para contestar una pregunta geométrica me sirve un input dinámico. Y para contestar una pregunta dinámica me sirve un input geométrico. Y terminé exactamente a tiempo.
Completamente. Es bueno. Pues hay tiempo para la pregunta. Hoy seguimos inmediatamente después. Pablo.
En el caso del toro, entonces había esta dicotomía periódica o densa ergódica. Y estaba dictada simplemente porque la dirección fuera racional y irracional. En el teorema de Beach se recupera la dicotomía, pero no se habla nada sobre irracionalidad y racionalidad de la dirección. Hay una,
Sí, no,
se
pero
puede caracterizar, por
sí.
ejemplo, la clase de superficies para los cuales corresponde otra vez a ser racional y
Sí,
irracional.
bueno, no va a ser racional y irracional en general, pero lo que sirve es esto, básicamente. Si tú vienes a dirección, tienes una conexión de silla, entonces tu flujo es periódico. Si no tienes conexión de silla, es la otra. Y por ejemplo, si tú me das una superficie fácil, yo te puedo decir más o menos cuáles son. Entonces, por ejemplo, las que son cuadriculadas, como la L que yo dibujaba, ahí va a ser racional y irracional, básicamente. Porque el grupo de Bichos es un subgrupo de índices de 0, 0. Pero, por ejemplo, si lo haces con el octágono, ahí te lo puedo decir, porque es como si la pendiente está en cura IC2, entonces, depende un poco de la superficie. Pero, pues sí, uno puede hacer.
Andrés, ¿usted se acuerda de cómo era que se llamaba el operador J que trabajaba con Encuentro?
Una variante real.
J invariante.
Sí.
Hay un profesor de la Universidad Autónoma de México, se llama Tim General, que
Sí.
fue tesista de Quillen. Y que él trabajaba. De Sullivan, perdón. Y que él trabajaba con las decomposiciones más sencillas que tenemos nosotros ahorita, las del toro, con las direcciones racionales y irracionales. Entonces usaba números periódicos y cosas de estas para conseguir unas simetrías de un operador J. Y yo quería saber si existe algún equivalente de esta construcción para superficies de traslación diferente con otro tipo o para otros puntos del espacio móvil. Si usted sabe de eso.
No sé. Lo quería mirar bien qué hace.
Ok.
Pero en general los operadores diferenciales no son muy bien portados en la superficie de traslación. Por ejemplo, en la ablación es superficie es más fácil en espacio módulo y no es tan difícil. Paradójicamente. Pero en una superficie es muy difícil porque pues, son planos, pero tienen estas singularidades. Entonces, desde el punto de vista del análisis es muy difícil de adaptar. Forni tiene varios artículos de eso, pero son muy difíciles.
Una pregunta más curiosidad. Por ejemplo, está la órbita, ¿cierto? Ajá. Entonces, ¿hay algún resultado si, por ejemplo, yo cada cierto tiempo me paso a una órbita cercana con una perturbación? ¿Algún resultado para la dinámica? ¿Sigue siendo periódico? Pues, ¿o has visto algo así?
Sí, pues más bien al revés, como que uno puede, por ejemplo, tomar órbitas de ese estilo y aproximarlas por una órbita en concreto. Digamos, puedo tomar como, sigo una órbita por un tiempo, después curvo un poquito, tomo otra órbita, etc. Y eso lo puedo aproximar con una órbita sola. Ese tipo de cosas la puedo hacer. Pero si cambio es así, digamos...
Sí, perturbaciones pequeñas.
Sí, no, perturbaciones pequeñas se puede hacer, pero por los casos, cuando uno hace una perturbación, usualmente cae como en el caso general. Entonces, el caso general es que la órbita va a ser como que va a haber todo el espacio, no se va a escapar infinito, va a moverse a todo espacio. Y va a ser, bueno, la palabra de que va a ser mixing. Entonces, eso es como el caso general que pasa.
Okay, so más preguntas después. Now we switch to English and we'll go to the next lecture. Thank you very much. It's my pleasure to welcome here Manuel Rivera from Purdue University. So, and now he's in the house now for this year. So Manuel has just started here at the Universidad Nacional de Colombia for 1 year. So Manuel attended graduate from MIT, first of all. Then he went for his graduate school at CUNY Graduate Center. He was a student of Sullivan, who was also mentioned just a few minutes ago. So Manuel was a student of Sullivan, And then after that, after his PhD at CUNY Graduate Center, Manuel has been a visitor in Paris, in Jussieu, at Cinvestav, in Mexico City, at the University of Miami. And now he's currently professor at Purdue, and currently visiting us here. So welcome, Manuel.
Thank you. Yeah. Okay. Yeah, thank you for the invitation. It's a pleasure to be here. I'll be here for 1 year. Voy a estar por un año. Si quieren hablar, si quieren discutir, me dejan saber. Okay. So I will talk about symmetry and structure in loop spaces. I'm an algebraic topologist. So this will be my point of view and my language. But first, let me say something about my connections with the Universidad Nacional de Colombia and Colombian mathematicians. I'm not from Colombia, my wife is. So I'm from Puerto Rico, yeah. Sure. I've been interacting with UNAL and Colombian mathematicians for about 15 years now. I've been 15 years with my wife. So, she's from Barranquilla. So, and I should say that there's a successful partnership between my institution and UNAL and other Colombian institutions. Basically, there's a partnership where undergraduate students in their last year, I think, spend 6 months at Purdue writing an undergraduate thesis, and this has been very successful. We've had many students from Colombia, many in our department. Sometimes they stay and they finish their PhD at Purdue. In particular, today I will present some joint work with my former PhD student, Daniel Tolosa, who was an undergraduate here at UNAL Bogota, and now he's at Arizona State University. And maybe some more connections. 2 years ago, we organized a geometry and topology meeting here in Bogota at this campus. This was the first iteration of an event that we plan to organize every 2 years. We had the second iteration last week in Cali, which was strangely memorable for obvious reasons, but also a very, very successful event. Yeah. Okay, so let's get into the math. So maybe the motivation. So the basic idea behind my talk is to understand or study geometric space by probing it with loops. So more precisely, here are some motivating questions. Given a topological space X, there you go. Given a topological space X, possibly equipped with additional structure, this structure can be a combinatorial structure, like a cellular structure, a simplicial complex structure. It can be also a geometric structure, smooth structure, a symplectic, a Kähler structure. So we may ask, how does this structure manifest at the level of loop spaces? So the loop space of a topological space is the space of all continuous maps from the circle into that target space. That has a natural topology, the compact open topology induced by the underlying topology of X. Okay, so we can ask, how does geometric structure manifests at the level of loops? We can also ask, can we understand this infinite dimensional object? So if, for example, if X is a finite dimensional manifold, one can interpret the loop space as an infinite dimensional manifold. Can we understand it from finite combinatorial data and efficiently compute invariance from some model generated by finite data? All right. And we can ask, what does the structure of the loop space tell us about the underlying space itself? Okay. Can we extract new, for example, manifold invariants by looking at loops in certain geometric space, by looking at the algebra of loops in certain geometric space? And in this talk, I will discuss certain interlocked combinatorial, algebraic, and time-permitting geometric structures and symmetries associated to loop space. Okay, with these questions in the background. Good. So we start with some combinatorics, some combinatorial models for loop spaces. So suppose I'm thinking of a topological space presented by a combinatorial structure. For example, a simplicial complex, a space built by gluing simplices along their faces. I will describe a construction of a cellular space, this L cubed K, such that these bars denote the geometric realization. Okay, so any space built by cells, you can think of as a combinatorial object, or you can also think of a topological space. When I use these bars, I mean that I'm thinking of them as topological spaces, geometric realization. So given a simplicial complex K, I will describe a cellular space, this L cubed K, such that the geometric realization of that cellular space is exactly the loop space of K, okay? And this space, or this combinatorial object, will be directly determined by the combinatorics of K, okay? So if K is presented by finite data, that finite data will generate all the homotopy type of this loop space. And the idea is the following. The idea is that the cells in this combinatorial object will be labeled by what I will call necklaces in K. I will explain this in more detail in my next slide. But basically, necklaces are closed strings of simplices inside K, such that, or a sequence of simplices such that the last vertex of one is the first vertex of the next one, and they close together, forming some sort of loop. I will discuss this in more detail in my next slide. And the point is that these necklaces can be regarded as families of loops inside K, parametrized by certain polytopes that will have some interesting combinatorics. These polytopes that arise will be of independent interest. So what are these necklaces? Okay, so in order to make sense of necklaces, I have to first choose a coherent ordering on each simplex of K. That means an ordering of all the vertices of each simplex that is coherent, right? So the ordering, if two simplices share a face, the ordering induced by the two simplices on that shared face is the same. So it's a coherent ordering on each simplex. So what are necklaces? Necklaces are objects that look like the following picture. Okay, so a necklace will be a sequence of simplices. Remember, every simplex has an ordering, total ordering of the vertices, such that the last vertex of each simplex is the first vertex of the next one, and they closed in this form. That's a necklace. So I'm considering the totality of all these objects inside your simplicial complex. And there's some rules, okay? So first, every necklace will have I call these simplices the beads of the necklace. Every necklace will have a marked bead, like a pendant, right? A special bead. And there's two more rules. The marked beads can be simplices of any dimension. So Kn denotes the n simplices of K. So they can be zero simplices. They can be vertices. Now, the ordinary beads that are not marked cannot be of dimension 0. They have to be of positive dimension. And the one simplices in the beads that are not marked, the edges, can be, we think of these edges as two-way streets in your simplicial complex. So if you see this edge here, that orientation might not appear in the data of the ordering of the simplicial complex. It might go the other way. In other words, these beads take values in all positive simplices or these formal inverses for the one simplices. That's what I denote by K1 up, right? So the point is that these one simplices are two-way streets. You formally invert them when you're considering necklaces. Is that clear? So that's a necklace. Okay, so I'm considering the totality of all of these. And the point is that in a simplicial complex, a simplex is like a family of points, right? Now, in this model for the loop space, a necklace will be a family of loops. So these will represent certain cells in the combinatorial object that I'm constructing.
Are you allowed repetitions?
Sorry?
Are you allowed repetitions?
Yes, yes, of course. Yeah. You're allowed to go.
So there are infinitely many.
Infinitely many. Yes, exactly. In fact, the information of the fundamental group is encoded here. So you can, right? Because these edges have two-way streets, so you can keep iterating and go around many times. Yes. So these are necklaces inside a simplicial complex. Okay. So first notation, necklaces will be denoted by this notation. So the sigmas are simplices in K. The sigma 0 that appears outside is the marked bead. Okay. And the sigmas that appear inside brackets are the beads that are not marked. That's the notation. And I'm going to define a dimension for necklaces. The reason for defining this number will become apparent later. The dimension of a necklace is the sum of all the dimension of the simplices minus the number of beads that are not marked. Okay, so the point is that these beads I will think of as families of paths of one dimension lower. But this bead will be a family of paths of the same dimension of that bead. This will become apparent in a second. Okay. So let me explain how to think of a necklace as a family of loops. So in order to explain this, I want to explain first how a single simplex can be thought of as a family of paths from the first vertex to the last. So in fact, that family of paths is parameterized by cubes. Okay, so the idea is that an n simplex can be decomposed into an n-1 cube of paths in a particular way. For example, if I have a 1 simplex, that's a path itself in K. So that's a single point. That's a 0 cube of paths. I'm thinking of that 1 simplex as a path going from 0 to 1. Now, a 2 simplex, I'm going to think of as a 1 parameter family of paths in the following way. I give you a parameter t, and I'll tell you a path from 0 to 2. How is that path defined? Well, you think of this edge from 0 to 1 as having unit 1, and you go t units in that direction, and then you go straight to 2. So as t varies, when t equals 0, I have this path here from 0 to 2, this edge, right? As t varies, I go up a little bit and I go directly to 2. When t equals 1, I have this path here from 0 to 1 and then from 1 to 2. So it's given by this picture, right? I'm thinking of this interval or this 1 cube as a family of paths. On the one boundary point, I have this edge, this path, right? As t varies, oh, I forgot to draw it here, but you can put this picture here, right? Forgot to draw the path. And then at the other boundary point, when t equals 1, I go up directly to 1 because t equals 1, and then directly to 2. So that's a particular way of decomposing a simplex into a family of paths from the first vertex or the 0th vertex to the last one. Let's do one more dimension, okay? The same idea can be generalized for higher dimensional simplices. So for example, the 2 simplex can be thought of as a family of paths from the 0th vertex to the 3rd vertex, parameterized by a square in the following way. I give you 2 parameters now, t1 and t2, and I have to describe a path. How is that path obtained? I start at the 0th vertex, I go t units in the direction of 1. Again, thinking of this edge as a unit, there's some reparameterization involved, of course. I go t units up, then I look for the next vertex, which is vertex 2. I go t units straight to that vertex. So this edge is in this 0, 1, 2 phase. And then I have no more parameters. I go straight inside the simplex to the last vertex. So given 2 parameters, I gave you a path, right? And that defines a particular way of decomposing an n simplex, the same idea, into an n-1 cube of paths, okay? And now you can analyze what happens when you go to the boundary, right? So for example, if t1 is 0, that means I don't move up, right? And then if I let t2 vary, I vary my path along this bottom face. That's if t1 is 0 and t2 is varying. So when t1 is 0, I'm in this phase, right? Assuming t1 is the x-axis. So this phase can be labeled by that bottom face using this previous decomposition. See, so they fit nicely in this way. For example, let's see what happens when t1 equals to 1. When t1 equals to 1 and I let t2 vary, so t1 equals to 1, it means I have to go directly to here. And then t2 varies, it means I go t2 units in this direction to the 2nd vertex, and then I go to the 3rd one. So I always have this first edge here, and then I cover this whole 1, 2, 3 phase with paths. So that's labeled by this picture, you see? How do you interpret this picture? It's the family of paths that starts here. There's nothing I can do here. And then you use the same idea in this previous picture for this phase, you see? So if you see, this family of paths has this labeling, and this labeling, the faces of this cube correspond to, I'm going to use this word that I haven't defined, open necklaces, namely necklaces that don't close, they're open, from the 0th vertex to the 3rd vertex inside this one-bead necklace. You think of the simplex as a one-bead necklace, as an open necklace, and then you look at sub-necklaces inside here. All the sub-necklaces are given by the faces in this in this labeling. You see, that's a sub-necklace from 0 to 3. This is also a sub-necklace, open sub-necklace. And then the vertices correspond to these necklaces of dimension 0 in some sense, okay? So we can decompose simplices into families of paths of one dimension lower. That's the first idea. Okay. So that's how I will, let me go back for a second. That's how I will think of these simplices that are not marked. Okay. The marked simplex has a different description, which I will describe now. And then I will concatenate these families of paths together. And that's what a necklace will represent. So let me explain how to think of a marked bead. This is acting a little bit funny. Okay, here you go. Okay, so the point is that an element in the loop space has a marked point. I'm thinking of the circle as having a fixed base point, and I can always evaluate a loop at that base point. Okay, so when I describe a family of loops, I have to tell you where the base point of each loop in that family is, and that base point will take place in this marked bead. So the idea is that on this side, I have the marked beads, and I'm going to think of these as families of paths as before, but now I have an extra parameter, the green parameter, which is the base point or a marked point in your path. So for instance, let me start here, which is the 0 simplex is sort of trivial. You're thinking of it as a constant path, right? So a 1 simplex, now I want to think of it as a 1 parameter family of paths with a marked point, right? I have a single path, which is the path from 0 to 1, but now I can vary the marked point, which is the green label, the green marked point, right? So now I can label the faces in the following way. At one endpoint, I can label it by this picture. This is like a necklace, open necklace, but now I have a marked bead, you see? The marked bead is saying that the base point of that path is there. On this other endpoint, I have another necklace with a marked bead. The marked bead is different. That marking is saying that the marked point of that path occurs at that point 1. And this edge here can be thought of as this 1 simplex, and it's marked because marked means that the base point is varying. Okay, let's go 1 dimension up. Maybe it will be more clear. I want to explain how the 2 simplex can be thought of as a family of paths with marked points. Okay, each path now has a marked point, so I have an extra parameter. First, I use the same idea as before to decompose this into paths. I have now 2 parameters, T1 and T2. The first parameter, T1, is the same idea as before. You're decomposing this simplex into paths, right? Now the second parameter, T2, tells you where to mark your path, determined by T1, right? So this T2 can take place at any point, can vary along this red path. And now we can ask the same question. What are the combinatorics of the object that's parameterizing these paths? As we pass to the boundary, what kind of picture do we have according to labelings of necklaces with marked beads? So let me explain the labelings here. The point is that now I have a subdivision that I will explain. So first, what happens when, let me explain this edge here. Why is there a subdivision here? This edge here corresponds to T1 being equal to 1, okay? So when T1 equals to 1, I'm looking at this path here, right? Because you go T1 equals to 1, so you go directly to 1. So I'm looking at this path. And now I let T2 vary along that path. But I have two options for T2. T2 can be on this side, or T2 can be on that side, right? Or T2 can be on the vertex. So that information I record as a subdivision of this edge, right? And at this point, I get the family of path. Well, not the family of path. I get this is a path, right? That is marked here. This is a family of paths. This portion where the marking is varying along this edge. And for this portion, I have this path where the marking is varying along the first half. You see? So that determines new combinatorics in this modeling polytope. If you play the same game, one dimension up, you get this interesting picture. It's a particular subdivision of the cube, right? Now I've highlighted two pentagons. And you can start studying the combinatorics of the objects you get. And these lead to a family of polytopes that we coined as freehedra. They also appear in the literature as Hochschild polytopes. Okay. So now that I have described how to think of marked beads as families of marked paths and beads as families of paths, let me explain how to think of a necklace as a family of paths, putting these ideas together. Okay, so I have a necklace, and now each bead, which is not marked, will give me a cube of paths of one dimension lower, right? And then this bead will give me a family of paths parameterized by these polytopes that I just described, a family of marked paths. So a necklace like this one will give you a family of paths parameterized by the product of all of these cubes together with the polytope, which the freehedron corresponding to this vertex. So in this particular picture, so this, I have no parameters. This is a 0 cube. This is a 2 cube of path. This is a 1 cube, 0 cube, 2 cube, 1 dimension lower, 0 cube. And this is a 2-dimensional freehedron, which was a pentagon. So this picture gives you a family of paths parameterized by this 8-dimensional object. Remember, this is a subdivision of the square. It was a pentagon. So for example, given 8 parameters, T1 up to T8, I have described here, this is a picture of the path, of the corresponding path, putting the previous ideas together. In this case, T2, the second coordinate in this polytope, is what gives you the base point of the path. So the path starts here and goes all the way around. You see? So a necklace is a family of loops with a base point, and the base point varies in the marked bead. So for every necklace, I have this subdivided cube. And the idea is, so for every necklace, I have this thing. So this is the dimension of the marked bead, and this is the sum of all the dimensions of the beads that are not marked. For every necklace, I have a cell, and I'm going to put all of these together by looking at the necklaces, all the necklaces inside your simplicial complex. And then I'm going to paste them according to how necklaces fit together, according to inclusions of sub-necklaces, and so on. These necklaces define a pose set, right? Just by inclusion of sub-necklaces. I have to appropriately define what an inclusion of sub-necklaces is. The marked beads are preserved, and so on. And that leads to this gluing data. And I have a space, or a cellular space. I have a polytopic complex, where the modeling cells are these Cartesian products of polytopes. Yeah.
So your college is a free-hedron, and you're saying that it's polytopic, and I assume you know how to prove it, but how hard is it to prove that this cubical complex can actually be realized as a...
Yeah, it's not trivial. I didn't do it. It was done by Polyakova, by Dasha. Yeah, it can be realized by a convex polytope. So it's a good question. Yeah. I'm thinking if it can be realized by vertices with integer coefficients. I'm not sure, but maybe, I think. It's, I have pictures. Yeah. And what's the theorem? The theorem that we proved is that for any simplicial complex K, there is a homotopy equivalence between the geometric realization of this polytopic complex and the loop space of the geometric realization of the simplicial complex. So in particular, if I want to extract information about homotopy invariance, like homology, cohomology, and so on of the loop space, I can do it from this combinatorial objects, right? Because that contains all the homotopy information of the loop space. Yeah.
Can I ask another question? So the parameterization gives you these very specific paths. And
very specific, yeah.
And so is the content of your theorem somehow that, I mean, all the other loops that you could realize that are not.
You can deform them to these things in a coherent way. Yeah, yeah, exactly. Precisely.
Whereas it's not possible to deform them just into paths that go along the one skeleton.
Well, I think you need the higher dimensions of each simplex in order to get the right homotopy type. Yeah, I think if you do that, you can get probably the fundamental group at that level. But in order to get higher homotopy groups, you need to consider the full dimension of every simplex. Yeah. Exactly. That's like a first layer approximation. And you can, for homotopy equivalence, you have to consider.
Yeah, on the face of it, it looks funny that you have all these families of paths, even though they're all homotopy equivalent to each other. And I guess when you globalize,
yeah, exactly.
They're not
exactly. Yeah. So let me switch to some algebra now. How does this connect with algebra? So how much time do I have? When do I stop?
I think it's 35.
35. Okay, so let's see how far I get. So let's discuss some algebra. Algebra behind the previous construction. Okay. So I said you have this combinatorial object that encodes the homotopy type of the loop space of a simplicial complex. The combinatorics is determined by the underlying combinatorics of the simplicial complex. And from this object, I can extract invariants such as homology and cohomology, homotopy groups, and so on. For instance, homology can be extracted from the cellular chain complex of this cellular complex or this polytopic complex. So I want to describe the cellular chains in a different way that will connect with some algebraic constructions that appear in other fields of mathematics. So it's a very interesting connection. So first, let me define this bold ln of k. I'm going to linearize my construction. So I'm going to consider linear combinations of necklaces in k of dimension n, right? And I'm going to define a differential. So what do? You take, these necklaces are like cells, right? So you take the signed sum of the faces, appropriately signed, right? Just like what we do with simplicial homology and so on. So I'll say it in the language of necklaces. Given the necklace, you have to determine these signs appropriately, but you look at all codimension 1 sub-necklaces inside N. And you have to figure these signs appropriately, right? Or you look at all necklaces N prime of dimension 1, or N minus 1, if N is of dimension little n. Equivalently, this differential is given by the signed sum of the faces of the corresponding, I should have said free hedron cross cubes, right? Remember, every necklace corresponds to the product of a free hedron and a cube. So you can think of that in that way. And now you can check that d squared equals 0, as usual. So that's a chain complex generated by necklaces. So I'll denote by L bullet the direct sum of all of these. And the amazing thing is that this construction that I was just describing is determined by a more fundamental construction through an algebraic functor, some natural construction. You can apply it to the chains on K. But you have to consider the chains on K not only as a chain complex, but as a differential graded coalgebra. Okay, so the chains on any simplicial complex has this coalgebra structure that I will recall, usually called the Alexander-Whitney diagonal approximation, which is what dualizes to the cup product in cochains, in simplicial cochains, right? It's a particular cellular approximation of the diagonal. And that data determines functorially the chain complex that I just described in terms of necklaces. So let's recall this construction. So K is a simplicial complex with, remember, an ordering of every simplex. So Cn is just the linear combination of the n simplices. I put them all together. Partial is the usual simplicial boundary. I'll just use the given by the alternating sum of the faces. Delta I is the face opposite to the ith vertex of sigma. And you have a coproduct, a 1 to 2 map. That's a coproduct, which is graded, right? Something of degree n here goes to a sum of tensors that add up to degree n. And that coproduct is given by this map. So this notation means sigma is a simplex. This notation means I restrict sigma to the face spanned by vertices 0 to I. So this is the first I-dimensional face, and this is the last n minus I-dimensional face. So that's a coalgebra, and these are compatible. This satisfies the dual of the Leibniz rule. The Leibniz rule from calculus, you can look at the dual, you can reverse the arrows, and these are compatible in that way. That's the requirement for being a differential graded coalgebra. And now the theorem, there's a word here that I haven't described, and I will describe it in the next slide, is that this complex of necklaces, remember, this is generated by all necklaces inside K, is naturally determined by this data through a purely algebraic construction that makes sense for every differential graded coalgebra. This algebraic construction is called the Hochschild complex of a coalgebra. And there's a step that you have to add, that it's formally inverting one simplices. Remember, that's not encoded in this construction. So you have to remember the data of the one simplices. So let me say a little bit of what this construction does. It's a construction that was defined in the context of homological algebra, independent of all of these discussions. Okay, so the Hochschild complex. So again, this is a purely algebraic construction. So let me just describe it, and I'll say something about the meaning of it later. So C partial delta is a differential graded coalgebra, and this curly C will denote the Hochschild complex of a coalgebra. So I do the following, and this you might recognize this. So so I take a copy of C, which is like playing the role of the marked bead, and then I take monomials on a shifted copy of C. So everything that was degree n here in this S-1 becomes of degree n-1, right? Like that was the same shift we saw in the necklace construction. Remember? So I take this abelian group. I'm working over the integers, but this works over any ring. This coalgebra can be defined over any ring. And then I can define the differential. Okay. So there's a little detail I'm sweeping under the rug. Remember, when I take sequences of simplices, I want them to match. Here, if I take the tensor product, I'm not requiring that matching. But I can change the definition of this tensor product. I can work over a fixed set of vertices and make this C what's called a comodule over a fixed set of vertices. And then I take the corresponding operation in that world. And this ensures that sequences of simplices match. Right. Anyway, that's a little detail. And then I can define the differential. The differential, so here's a formula, don't get scared. Look how I'm denoting the generators here. I'm using the same notation as before, right? This x0 corresponds, is an element in this extra copy, and this is a monomial, and the brackets denote that they're shifted. So the differential is obtained by applying the underlying differential and the underlying coproduct in an appropriate way. So there's signs that I'm ignoring. You apply the differential in all slots. Now I'm writing the coproduct in this way, abusing a little bit notation because this is supposed to be a sum of tensors. And I apply the coproduct in all, I split in all possible ways. And then here at the marked point, I apply it in this way. First, I push this second factor here, and then I push the first factor around.
What is it doing geometrically? It's pushing around.
Yeah, it's exactly looking at all marked subnecklaces of a necklace. That's the theorem.
But
Let me just say something. The theorem is that these two things are enough to recover all subnecklaces inside a necklace of codimensional 1. This coproduct is the splitting, this formula that I wrote generates all possible sub-necklaces in some way.
But did you give us a definition of subnet?
I did not.
Ah, okay.
But I can tell you in words, it's a sub-necklace is a sub-necklace. Such that the mark beats are preserved. The mark beats of the smaller thing is inside the mark beat of the big thing.
Okay. And the rest is just
sub-simplices of the beats, right?
and you can reduce the number. So if you
Yeah,
have
you
7
can reduce
beats,
the number, you can make it longer.
oh,
Yeah.
the subnecklace you can have longer.
Yeah, because you can look at a path inside a 3 simplex. Take a 3 simplex. That's a 1 G.
Yeah.
Right?
Yeah.
But inside you can look at the path from 0 to 1, 1 to 2, 2 to 3, and consider that as a necklace with 3 beads. That's longer, but that lives inside.
Huh.
But the dimension, in the way I defined it, it's smaller. Right? So what's the theorem? So maybe a word about this construction. This construction has an interpretation in homological algebra. It's modeling, if you know some homological algebra, it's modeling some derived cotensor product in the category of coalgebras. But I don't want to go into these details, but it was born outside the world of loop spaces. So what's the theorem? Well, the theorem I stated before is that if I plug in here the simplicial chains, and I do a little bit modifications of including these inverses, I get something that's isomorphic on the nose to the chain complex of necklaces. So the theorem is that this differential is giving you all sub-necklaces when the x's are simplices in K. That's the theorem. It's recovered by this construction from homological algebra. So let me say some more words about algebra. Okay, so this fits in a duality theory. So the same construction that I just described for coalgebras makes sense for algebras, for differential graded algebra, right? When we defined the differential of this Hochschild complex, we were splitting things. If you have an algebra, the differential will multiply things. Okay, so you can define an analogous chain complex for any differential graded algebra. And these two constructions of algebras and coalgebras are related by a duality theory that's very subtle. It's not just dualizing as taking linear dual. It's a different duality theory. It's called Koszul duality. And it's given by these two constructions called cobar and bar. This is cobar, takes a coalgebra, produces an algebra. And there's a bar construction, takes an algebra, produces a coalgebra. So let me just say in words roughly what these constructions do. If I take a coalgebra, which has a differential as well, I can construct a free algebra on the underlying abelian group, graded abelian group. I take monomials. That's an algebra. And then I use the data of the differential and the coproduct to define a differential in that free algebra. By Leibniz rule. And with the right grading, that becomes a differential of degree -1. That's a construction. I take a free algebra and I use the data of the coproduct to put a differential. And I can go backwards. If I have an algebra, I can for a second forget that's an algebra. I just consider as an abelian group or vector space or module. I take a free co-algebra construction, and then I use the algebra to define the differential, the algebra information. And these define an equivalence in a suitable sense of homotopy theories. It's not an equivalence of categories. It's in a suitable higher sense, because here I have notions of equivalence which are weaker than isomorphisms. And now these two constructions that I described are related by the following information. So I can take a coalgebra C. I can apply this, because I make it bigger. I take monomials, and I get an algebra. I can take the Hochschild complex of that bigger algebra, and that's equivalent to the chain on the Hochschild chain complex of a coalgebra. But this equivalence is a quasi-isomorphism. What does that mean? That there is a map of chain complexes that induces an isomorphism on homology after I take kernel mod image. That's my notion of equivalence in this world, right? And similarly, I have a quasi-isomorphism if I start with an algebra. It's a duality theory. So what can we do now? I can start with a simplicial complex K. I can look at the chain complex of necklaces. I know this computes the homology of the loop space of K, right? So I said the theorem was that this construction is given by applying the Hochschild chains to this coalgebra. And I put a hat because the hat means one must invert one simplices appropriately. And then I have a Kosul duality theory that gives you that this is the same as the Hochschild chains of an algebra. This algebra is a free algebra as an underlying algebra, is a free algebra on this thing, on this graded module or vector space. If you're over a field, you take the free algebra. The hat means that you have to localize, you have to invert the one simplices in that algebra. That's what the hat means explicitly. And then there's a differential determined by the co-product of this coalgebra. So this is a bigger thing that's computing the same homology of this smaller thing. That's what I just said. It's a thicker model, right? Here you started with a coalgebra, now you make it bigger, and then you take a construction which is bigger, this Hochschild construction, but it still computes the homology of this thing. And you can ask, what's the combinatorics behind this construction, right? For this construction, it was controlled by these free hedron and cubes. So you can ask, is there an analog for this bigger construction? And the amazing thing is that we discovered a very interesting family of polytopes that play the same role as the free hedron played over here. In other words, this bigger chain complex can be realized as the cellular chains of a new polytopal complex built by gluing Cartesian products of cubes, but instead of prehedra, now I need a bigger thing, bigger in an appropriate way. I'll describe in what sense. And these polytopes that arise that control the combinatorics of the boundary of the differential here turn out to be self-dual polytopes. And this is a very rare property to find in nature. Self-dual means, so if you have a polytope, you have a face lattice, right? You have a poset that completely encodes the combinatorial type of the polytope, where the elements of the posets are the faces, and then you have inclusions. Self-dual means that the face lattice poset of a polytope is equivalent to its opposite. It's like Poincare duality. So these self-dual polytopes come from a family of polytopes that we have coined as Goodwillie polytopes. The name Goodwillie is there because this kind of model for the free-loop space in a different way was considered by Tom Goodwillie previously. I'm not sure if it's a great name because it's a kind of a long story to get there, but and their combinatorial properties are interesting and of independent interest. So I want to describe a little bit these Goodwillie polytopes. I'll take a few more minutes because if you click here, how do can someone help me? That's a link. And how do you? So this was done by Daniel Tolosa, my student. It's like visualizations for these Goodwillie polytopes and how they relate to the prehedra. So for example, so there's an explicit description of these Goodwillie polytopes, which I'm not going to go through. Is you start with the cube and then you add certain vertices. But let me show you a picture. So that's the prehedra, and you thicken it, and you get this polytope. Remember, the prehedra was a subdivision of a cube, and then you can thicken it in the way it was described here to get this polytope. This is and you can glue all of these cross with cubes to obtain a model for this bigger model for the loop space, but it has an interesting symmetry now, right? The modeling cells have this interesting symmetry. The symmetry is that these are self-dual. In particular, let me see. Okay. That's a prehedra, and then this is the thicker polytope. Right? It has a different combinatorics at the prehedra. In particular, those orange vertices were newly added now. So there's more things to play here. For example, you can look at the phase posets at let's do that dimension 4. That's a phase poset. In particular, since these are self-dual, the phase vectors are palindromes. The phase vector is when the vector that you get by, so this is the empty phase, was always 1. Then you put vertices, how many vertices? How many edges? How many 2-dimensional faces? How many 3-dimensional faces, and so on? So the self-duality means that these vectors are self-dual. These are the computations of the first few. You can see they're all palindromes. And so how do I get back to, I'll finish once you go back to the presentation. So there's a website that you can play around with the combinatorics of these Goodwillie polytopes, that their combinatorial properties are of independent interest. And now let me say one more thing to finish. Maybe I'll say this in words because I have a few more slides about geometry, but where do we want to use these models? Okay, so there's this field called string topology. String topology is about interactions of loops inside a smooth manifold, right? String topology, it was born with Chas and Sullivan, and the idea is that if you have a smooth manifold, you have transversal intersection and transversal approximation in a smooth manifold. And now you can use that transversal intersection to construct algebraic structures on loops, on families of loops. And then you can use the language of algebraic topology to describe interactions of loops. You think of families of loops as chains, or singular chains, or cellular chains in the loop space, and then use the smooth manifold structure to intersect them. And this connects with mathematical physics, connects with even mirror symmetry, and so on. So the idea, so that's a very rich subject. It's about the algebraic structure of the loop space. The idea is to use these models, these combinatorial models, to describe the structure inside of interaction of families of loops. So what do we do? And this is the program. Now you add to K, or to the chains on K, more structure. For example, you can add Poincare duality. You can add the K-Rip package inside these construction. And you can ask, what's the structure that these things induce at the level of loops? And these models let you compute efficiently these structures. And the point is that you can extract new and interesting manifold invariants by looking at these constructions in the loop space. And these combinatorial models provide you to do that, allow you to do that efficiently, just by looking at the underlying structure on K. Okay, so that's the program where these combinatorial models are used. So I think that's all I'm going to show you.
We have some time for maybe a quick question. But of course, yeah.
Two questions.
Yeah.
First, family of necklaces. Necklace has, I suppose, sub-necklaces. Is it hereditary, or there is a notion of necklaces?
Yeah.
Okay. There is a notion of, is there a property of joint embedding if you have two different necklaces? There exists bigger necklace where they are sub-necklaces?
Like a lattice or
something, let's say.
Not always, because they can be very far apart in a simplicial complex. But maybe it depends on the combinatorics of the simplicial complex, right? No. But
okay.
Well, you can let me. No, not always. Yeah.
Maybe
there can be necklaces that cannot be joined.
It depends on what you mean by join. You want to join them such that they fit inside a bigger necklace? I think, I'm not sure. I mean, maybe since all paths are invertible, you can always connect two necklaces with a path, right? And maybe you can use the two necklaces and two paths that connect them to do a bigger necklace. I'm not sure what that.
Okay.
I'm not sure if there's topological information in this property.
Thank you very much. In the interest of time, we can continue the discussion outside. Thank you very much.
Hablamos, es aquí un año. Creo que los huevos.
No hay una manera canónica en la que los puedan usar. Como si hay unos simples. Exacto. Si yo tengo dos simples o dos empleados simples, puedo construir una buena, simplemente pensando en las instrucciones de la cara de lo que con los mecanismos que se pueden. No habría una manera de algo parecido. Ok, pero si me dices por dónde voy. Bueno, es lo primero que con los grafos se puede hacer. Tienen los grafos que los contienen como sus grafos. Con los poliedros que la familia de los grafos, en términos de entonces tú puedes construir el límite en términos de lógica. Pero esa construcción el límite de Riese es una estructura que contiene una copia de todos los grafos. En el caso de todos los grafos que existen. De todos los grafos que existen. Pero además, o sea, ¿hay alguna noción así para politopos? No sé. Porque estos nécleres, no sé. Pero puede pensar como politopos. Ok. Que toda la información combinatorial de los subnécleres está codificada en la politopos. Las caras corresponden a subnécleres. Así que puedes pensar lo mismo. Ok, entonces lo que habría que pensar es, porque con politopos los sospechos de tipo son casos particulares de como de empleo artificial. O sea, realmente lo que te tienes que ver es si cuando tú traduces la parametrización a politopo, esa parametrización cuando tú pegas se preserva de alguna manera. Ok, eso me da toda la información combinatorial. Eso me da esperanza. Eso me da esperanza. Porque con los poliedros se puede hacer seguro. Muy probablemente se puede hacer con los politopos. O sea, así como hay información. Ok, tú puedes considerar, lo que sucede es que estos objetos que son numerables, que son estructuras grandotas en términos geométricos, son muy interesantes. Para empezar, son objetos que son random. O sea, ese límite de Riese es esa cosa que le interesa a los lógicos, a mí me interesa como geómetra y como topólogo, porque eso es el grafo de Erdo, aleatorio. Si tú haces eso con poliedro, obtienes un objeto que tiene una naturaleza aleatoria similar. Un poliedro aleatorio, o sea, cuando yo te digo que contiene una copia de cualquier poliedro, realmente eso es, esto es una trampa, porque esta es una proposición que es probabilística, o sea, con probabilidad 1 contiene una copia de cualquier poliedro. Ok, pero además hay un montón de gente que está estudiando esos espacios de otras maneras. O sea, hay topólogos que se teoría de Ramsey, o sea, espacios Ramsey, Todorce, Kevin, etc. ¿Qué se llama el otro nombre ruso? Es como Pesto, que trabajan en el script, que trabajan con los grupos de automorfismo de esa manera y que estudian cosas que son completamente porque eso, o sea, eso es una manera de evaluar, es una manera de traducir problemas de entropía. O sea, cuando tú coges cosas al infinito, es una manera de pensar en problemas de entropía de, por ejemplo, de dinámicas topológicas. Con eso se puede. Y eso, o sea, pero guarda. Si nada más te fijas en los simpleos, puedes definir este espacio. Sí, y guarda la información de las caras. O sea, el del límite guarda la combinatoria del simplejo. Guarda toda la información de las caras del aleatorio. O sea, no solamente los simplejos tienen esta propiedad de dualidad, de autodualidad. Ok. Eso se refleja de alguna manera en este espacio. No, el aleatorio no, el aleatorio es horrible. El aleatorio es un espacio horrible, pero es muy interesante topológicamente por eso, porque o sea, hay propiedades de entropía. Me gusta. Me interesa. O sea, esta es la primera pregunta que me interesaría saber. La otra es que de las últimas cosas que vi, todo eso último que estabas haciendo con la dualidad de cocinas, todo eso huele así de lejos a modelos minimales de grupos de motocuidad. Tú estás trabajando con eso. No, okay.
Todo eso está ahí.
Ok. Mándame una copia. Sí, claro, por favor, me interesa.
Claro.
Regálame un correo para fastidiarte después y te digo todo lo que quieras. Por favor.
Tú estás aquí.
Yo trabajo aquí en la casa. Obviamente.
Estamos más cerquita que.
Sí. Ahí donde quieras, no se me abajo.
¿De qué área vienes? ¿Cuál es tu background?
Yo hago topología algebraica.
Ah, bueno.
Sí. Yo me gradué en Francia con Saralegui, que es especialista de Héctor. Compañero, o sea, yo no sé si sea una tipaza, súper amable. Se llama Marta Macho.
Sí, claro.
Bueno, habían dos estudiantes, no eran compañeros de tesis, pero eran dos tesistas del mismo tipo en Francia.
Ella está en España.
Ella sigue en España, sí. Es un tipo muy agradable que se llama Lector. Y él es el tutor de él trabaja topología algebraica y yo hice la tesis. Entonces hablamos. Por favor, Gabriel Padilla, un placer conocerlo. ¿Cuánto tiempo va a estar? Por favor, pueden venir la semana que viene a nuestro seminario de topología y regalarnos una charla, un mini curso. Por favor, cordialmente bienvenido. Nos interesa mucho. Gracias.
The difference between the second and the last is I'm not sure. Maybe it's follow the doors.
No.
Victory, yeah?
Yeah. It's happy.
Follow the doors. Thanks very much.
Oh. Para que no.
¿Te consigo una cosa o no, huevo? No, ya lo vimos. Son hermanos.
¿Cómo? ¿Estás lista? No, conmigo. Simplemente decía la presentación. Sobre la presentación, hay que me la envíe a mi correo que ahí está abierto.
Vale. Esto ya le.
I think so. Yeah. It's strange because I've got the message from you go out.
Maybe there was a CC and that was the one.
It seems to be right. So, This was briefly, what? This was briefly. Oh, no, it's the okay. No.
You understood? Did you understand the test? Because I didn't understand. Everything is fine.
Hopefully.
Okay.
Sorry to interrupt. I just wanted to, we've never met, but I'm here to ask you student loan tutelage.
Yes, we talked about it.
Yeah, for a while.
So you're here now?
Yeah, down here.
You're in Los Angeles.
In Los Angeles, but in Bogota. Yeah.
Okay, great.
I started my second.
How's it going?
It's good. My Spanish isn't good fast.
I'm sure.
Yeah. I'm trying to maybe see for years.
How are you doing? So the idea, I'm not sure, Alex was telling me that we were feeling not great, but
Sorry.
okay. So the idea is perhaps in the afternoon to go to Los Angeles and perhaps
Right. Yeah, that'll be very
maybe the
nice.
Candelaria or something.
Yeah, that'll be very nice.
Great. So if we're a bunch of us here, we can either go directly there and have lunch there, or we can see. I'm not sure if you have plans with Andres or.
I was going to talk with Alex, Juarez a little bit after the talk.
That's great.
But otherwise, very happy.
No, I know tampoco.
Lunch here or there.
Sounds perfect. All right.
Hay una foto de, que está tomando de todos los participantes. O sea, hay una foto de todos los participantes para que.
Oh, okay. Just
Okay.
so photo group picture.
Pues entonces, si te interesa hacer una monografía en cadáver, yo te puedo mandar.
No sé si se me había cuenta la versión rara de
No, pues yo siento que perfecto.
Listo, vale.
Pues son, no sé si te explica.
La cosa es, que yo estoy
Realmente están en inducciones, entonces había
y llegan
la primera chica que me dijo,
oiga,
¿cómo ha sido? Del inducto.
y entonces yo resulta que lo que más o menos bueno, digamos que las ya saben sí, no, ya están metidos. Ahora como la cosa es, no, y ahora la cosa es como, bueno, ahora como que hacen no, más bien están ¿qué van? No, ya. ¿Yo?
Quiero que cada vez más.
Vamos a avanzar. Había un publicado.
Right, the salad. These are regular. No.
Probablemente lo que hacen para hacer un camino sencillo.
Cuando entonces podría ser, no sé, sumar la siguiente. En este caso, estamos esperando ya salimos, claro,
Before beginning and before introducing William Shopsky, I want to say something. I really want to thank many people here, and I will name a few of them. And one name Anyway, I want to thank, but I will, yeah, like people come in. I think it's important to mention. First of all, I want to thank my colleague, Alexander Cruz, who is here, who is the co-organizer, and also he helped me start thinking about this turn of the Encuentro since last year. We decided we wanted to continue with Encuentro, which has a very beautiful history, and then but make it, this celebration of the 70th birthday of the party. And I also want to thank all the faculty of Universidad Nacional de Colombia who participated in one way or another. Some people gave lectures, some people invited other people, some people, but there was a lot of presence of my colleagues from Universidad Nacional de Colombia. Thank you all. I won't name by name because it's too much, but I also want to thank you, all the visitors, especially for having come all the way to Colombia, people from different parts of the world, and really, I'm really thankful. I also want to thank Nicolas Nacher, the student, doctoral student, who was also, checking many details of what was going on in the last, especially in the last weeks of organization of the event. Of course, the Faculty of Science staff and everything with homepage, everything. Tanya, Jacqueline Carrasco, Henry Mora, Francisco Yus, and then students who volunteered to participate with all these tags, scarapelas and everything. Alejandro Munoz, Daniela Mortegui, Ivan Pinzon, and Jason Puerto. Really, thank you all, because without that, this event would not have taken place. I may be forgetting some people, some essential people, but really, I wanted to thank. Now, let's get to the important thing. So, it's really my honor and great pleasure to introduce Ehud Krzyzewski, Udi, as we call him, professor at Oxford, who is going to speak to us about, I guess the title is disappeared, but it's research for a small theoretic Galois group and approximate subgroups, right? Making the other one. To Krzyzewski, well, I just want to say very few words. So he worked in model theory, but his work in model theory has really reached many other parts of mathematics. Algebraic geometry, arithmetic geometry, methods of all sorts, and many other aspects that you might see along the way. He's now a professor at Oxford. He was professor at the Hebrew University of Jerusalem for many years, and before that he was at MIT also for a while. Without further ado, I just the floor.
Okay, thank you very much, Andres. Yeah, I was really very happy to get the mail from Andres and from Alex inviting me to the 70th year anniversary of the department. It's a great honor for me to be here. And also, even though in model theory, Bogota is really one of the great centers of model theory in the world, I somehow never had a chance to visit before. And in these days, it's been really wonderful to get a glimpse of the city and to see the hospitality and friendship of everybody. And also to listen to some great talks on diverse subjects. So, okay. I once received the advice, I think it was very common advice, that in one talk, you talk about one thing. You do not talk about two things. The problem is that the one thing I want to talk about is the connection between two things. So I'm not sure how, I'll try. There will be some slides about multi-theoretic Galois theory and some slides about approximate structures. And I will try to at least hint at the points of contact. So I'll start with very basic Galois theory. So we start with a polynomial in one variable, let's say over the rational numbers. And then you have the solution set. But the solution set, I'm not doing arithmetic now, I'm doing basic model theory. with the solution set, we do not, can be complicated inside the rational numbers, but we take a solution set within some algebraic closed field. Some field that is going to have solutions to equations if they can have solutions. You can take the complex numbers, or you can take some other algebraic closed field. In any case, for a single polynomial, if it's not constant or something, there are going to be finitely many solutions. Where should I look at this? Yeah, but so this is a set, it's a finite set. If you have a degree D polynomial, you expect D solutions. But it's not only a set, it's also a structure. You have several roots, you may have some polynomial relationships between them, or you may not. For example, obviously, we're interested to know if maybe this polynomial has a linear factor, then we'll see some element within this phi which satisfies x equals, I don't know, 2 or something. It might be that no, I mean, it might be that all the roots look the same, but maybe there's a situation that given one root, you can get another. For example, if the polynomial talks about nth roots of unity, so if you have one root, then the square of it is also an nth root of unity. Or you can have that the Galois group is a symmetric group and you see nothing, you have no polynomial relation. So this is something we're interested in, it's a structure. And here we see the basic duality of model theory, but model theory looks at relations. So it's not only elements of phi, but also n-tuples. And a relation is a set of n-tuples. Well, we're interested in ones that are definable by some formula. And that is the same thing as being invariant under the automorphism group of the structures, under the Galois group. Right, so this is basic Galois duality. When you go to infinite structures, it becomes a bit more complicated. The duality is a bit less immediate, but still model theory and group theory often have the role, some complementary roles. Yeah, so I mentioned the automorphism group of some finite set of solutions to some polynomial. You can also put them all together. You can take all the algebraic numbers. These are all the numbers in that field that have, in that algebraic closed field that satisfy some polynomial. And you can look at the whole automorphism group of this big structure. Now, there's a language to talk about it that it's a topological group. You can make a topology by saying that the set of all automorphisms that take A to B is a basic open set, And yeah, this on the one hand, it's just a language. It doesn't say anything more than what we had in the previous slide for each phi individually. The topology just helps you to know that your group comes from any finite group. But on the other hand, it is a useful thing because further in this talk, we'll generalize the notion of algebraic closure and of Galois group to include groups which are still compact, but no longer come just from finite things. They're no longer so finite. So this topological language is a bit more than just wrapping. Yeah, and I just want to mention between Q and Q bar, the Galois group is supposed to be important. So Q is arithmetic. When does a polynomial and many variables have a rational solution? That kind of thing is difficult. Q bar is geometry, also difficult, but somehow a bit less. You expect things to be a bit more decidable usually. And the Galois group is a thing that mediates between them, so people somehow have respect for this Galois group. They think if we understand this Galois group, we can understand more about number theory. So, for example, the Langland's program tries in particular to do that, explain it in some way. Okay. Yeah, I think I said already this thing, but But anyhow, everything that I've said so far, Galois theory from 1830 or so, actually generalizes to any first order theory, T. So the T that we had before, the theory that I was talking about was the theory of algebraically closed field. But if you take absolutely any theory, and again, there will be some duality between Galois invariance and between being definable. And once again, if you group together all the algebraic things, you get some structure, the algebraic closure. You have that, it's a compact group again that acts on it. And okay. Another thing, the way Galois theory is presented usually in undergraduate courses is the correspondence between closed subgroups and between substructures, right? And this also survives if you have a substructure. You can look at all the automorphisms that fix that substructure. And that, okay, if you do it just for a finite section, then it's a subgroup. If you do it for the whole thing, it's a closed subgroup. Conversely, if you take a closed subgroup, you can take all the elements that are fixed by that, every element of that subgroup, and you get some kind of correspondence. And it's a beautiful understanding of Shelach that, I mean, it would be really extraordinary for this to work for any first order theory, whereas we thought Galois theory was something special about algebra. And in fact, you need to change your point of view very slightly to make it true. You need to consider also imaginary elements. So it turns out algebraic closed fields eliminate imaginary elements, you don't need them. But in general, you have to think not only of ordinary elements, but also of classes with respect to definable equivalence relations. So one example of that is that if you take the integers, they don't include the rational numbers physically. 1/2 is not an integer. But nevertheless, you can think of it as an ordered pair of integers, modulo some equivalence relations, when A over B equals C over D, you can find the formula of that. And this is an example that you need to talk also about so-called imaginary elements that are there, but not as elements per se. And again, the generalization of what an imaginary element should be is part of what's behind the results in this talk. Right, so that was the introduction to the Galois subject. Questions? Okay, so now I'll go to the central object that the theorems will be about, which is the notion of an approximate group. So here's the definition. It's very simple. Yeah, no, I'm not talking about approximate subgroups. So I'm assuming given a group G, and we're interested in certain subsets of G. And for simplicity, I'm going to assume that they're symmetric and that they include the identity elements. Okay. And XX is just a set of pairs, not pairs, a set of products XY with X and Y in X. So what is a subgroup? A subgroup is a set X such that XX equals X, right? It's closed under the group operation. You don't get out of it. This is a subgroup. And in all the definitions of the groups, it was part of the definition of a group that somehow that operation, you don't only say there's an operation, you say it's closed under the operation. Anyhow, yeah. So first of all, two subsets, just to any two, let's say any two symmetric subsets, we say that they're commensurable if each one is contained in a finite union of translates of the other one. Okay? So this is a pretty familiar, in group theory, you say two subgroups are commensurable if the intersection has finite index in each of them. So you ignore differences of finite index. But when you write it this way, it makes sense for sets. You have a set, and you take the union of that with some translate. It's not that different. For example, the cardinality, these are finite sets. The cardinality, yeah, it could grow by twice as many or 3 times as many, but it stays in the same ballpark. Okay, and this definition was made by Terry Tao, that X is an approximate subgroup if X and XX are commensurable. And if you think about it, you'll see that it also means XXX, XXXX, and so on are commensurable. So, so this is an approximate subgroup. And in this talk, I'm going to talk a lot about trying to classify approximate subgroups. Of course, the trivial answer, not trivial, but an easy way to be an approximate subgroup is just to be a subgroup. So the basic case The uninteresting case is a subgroup or finite union of cosets of that subgroup. But there will be some other approximate subgroups, and we want to classify. Okay, I will say, yeah. So, oops. A lot of the literature, which I'll describe in a minute a bit, is about finite approximate subgroups. And in that case, you have to talk about families, not about single groups, because any single finite set is trivially commensurable to the identity, and it's not interesting. So you have to start talking about things uniformly. There's also a model theoretic way of doing it. If you want to talk about lots of finite structures, there's something you can use model theoretic compactness or a construction called ultrapowers to pass to a single structure which incorporates them in a uniform way. So if you show that something is an approximate subgroup in this limit, which I will not describe in detail, then that's the same as saying that the finite ones have this property, but in a uniform way. Okay, so yeah. Yeah.
Why do you have 3 x's in the measure one, but only 2 in the other one?
Well, so let's suppose now, yeah, so let me get to that. So as I said here, in the definition of approximate subgroup, if you have it for 2, then you have it for 3 or 4 and anything else. And now I'm going to define a slightly weaker notion in which, or yeah, you need to go to 3 so that it picks up. So anyway, sometimes when you can measure sets, you can define the measure of appropriate subsets of the group, including your basic set X that you're looking at, right? And sometimes you have a measure that gives X positive measure, and also gives X times X finite measure. This is not, this should not be taken for granted, right? For example, in the case of finite approximate subgroups, you can just take the counting measure. You can count anything, and yeah. So a slightly weaker condition is that X has positive measure and XXX has, well, finite measure. So in fact, if you want to say K approximate, if you want to make it explicit, at most K times, right? So it's clear that if you have an approximate subgroup, then it has this property. Yeah, if XX is unified to many processes, the measure is translation invariant, so it will not be that much big. But in fact, they're very close to each other. Yeah, I wrote you a lemma. Oh, no, sorry. So maybe, yeah. So maybe I think 3 are enough, but in this lemma I wrote it with 4. Yeah, so you can see that if you say, okay, X, I'm interested in X, but I'm interested in it, I'm willing to pass to X times X, they have a similar size. So this condition that that the measure of a finite attempt to close up X doesn't grow very fast, it implies that something very nearby is an approximate subgroup. I will not go into it. Okay. And this puts it into a very general and I think very fundamental kind of question in mathematics, namely, you have some structure, and for our purposes, which can be many things, it can be a category, an equivalence relation, many different things. And you look, maybe you look at some physical object and you see that very often it's closed under that operation, more than you would expect. For example, if you take some subset, some random finite subset of the reals, you would expect the size of it, well, the size of it, let's say it has n elements, you would expect the set of product to have about n squared over 2 elements, right? It would be very surprising if you have less. So the notion of approximate substructure here is that there is something surprising that X times X is not as big as expected. You get a surprise when you look at it. And then the question becomes, is there an actual subgroup or subring or whatever which explains it? Because you just got a set, you just kind of spoiled the set a little bit, you change it by a small amount, or is it a completely new phenomenon? So there's variations on what it means to be small. You could, if you have a set of size n, then you might think, well, okay, n to the 1 plus epsilon, or k times n. You know, for example, if you look at products of real, in a general group, you might expect there to be n squared different products. So if you see n to the 1.9, you might already think something's happening. For the various regimes, yeah, so let me give some examples of that. These slides will not be necessary for the rest of the talk. I'm just giving some background. So one kind of structure is that you just have m, let's say 2 functions, or maybe 2 invertible functions. It's like an action of the free group on 2 elements. You just, the structure, what is the operation, just go from x to a times x, and from x to b times x. That's it. So in this case, you expect there to be, well, if there are 2 functions, you expect there to be, you expect a given set to double its size, approximately. And if you see that it doesn't double its size, it always stays, of course, n to the 1.001 times that size. Yeah, I think you see I wrote n to the 1 plus epsilon twice. And I'm sorry, what I actually meant is here n to the 1 plus epsilon. Okay, so if you just have 2 functions, you would expect the maximum you could possibly have is 2 times n. And if inside that, instead of that, you see 1.1 times n, then you think something interesting is going on. Okay, so this is the notion of an expander to construct an action of some finitely generated group. Let's say SL2Z, it has some finite number of generators. You just, if it acts on something, it's just finitely many unary functions. And so it's very interesting. It has vast number of applications in computer science and other areas to have expanded. It means actions or graphs, but let's say actions which have no approximate substructures. If you take any subset of reasonable size and you apply the functions to it, it's going to be about twice as many, let's say. It's not going to be 1.001 many. The boundary cannot be very small. That's the notion of an expander. Kolmogorov defined it originally in the interest of thinking about the brain, about the kind of network that neurons must be in, and he proved probabilistically, I'm not sure I got the spelling here, right? Okay, they proved probabilistically that these exist, and it was Margulis who first, in 72, who first found an explicit example. Yeah, and Freiman studied just this growth subgroup. Yeah, so subgroups of Z. Z doesn't, you know, I mean, Z doesn't have finite subgroups. But if you look at the set of elements from minus 1,000 to plus 1,000, and you multiply it by itself, you will only get some set which is twice bigger, right? It will be the element from minus 2,000 to plus 2,000. So it's in that, it's in this K time. Yeah, so the need for it appeared in harmonic analysis, Fourier series, and Freiman classified all the approximate subgroups of Z in this sense. Yeah, so Erdős and Severide proved it for approximate rings. It's, you know, it's very obvious the real numbers don't have finite subrings. But if you talk about approximate subrings, it's not that obvious. You know, what does it mean to be a subring? It means you should be closed under both addition and multiplication. So approximate subring should be almost closed under both addition and multiplication. Not always, but you know, almost makes you think of 99%. You are talking about 1%. But even being 1% closed is very surprising. So they proved that there are no finite subrings of R, and then Bourgain Katz-Tau in a very, very influential paper proved something like that for finite fields. Yeah, maybe I'll jump straight away to say that the conjecture around Erdos-Semerezi, which was very widely believed, was that, in fact, if you have a finite subset of the reals and you apply both and multiplication, then one of these should raise it almost by squaring. You know, it would be surprising to have a set which only grows by a factor of 1.9. And this was very widely believed, but very recently disproved by 4 human beings. The following, but it's very close to a counterexample that was found by GPT a little bit before. Still the machine basically collated in a very intelligent way things that people had done before, such as Sokorevich, but anyway, it was a machine that did it. Okay, also a lot of results about, okay, so this is in blue because we're going to get to it later. We're going to try to generalize it to the non-commutative case, and also because this one is not about finite approximate subgroups. It's about approximate lattices, which are not finite. And there was a lot of work finally saying a lot about finite approximate subgroups, essentially classifying the linear ones. And this has had vast applications, which maybe I will skip, but it's really impressive to how many fields of application. And I would recommend a survey article by Emmanuel Brouillard. If you look up Brouillard and survey on approximate subgroups and application. Okay, so that was an aside. And now I'm back to approximate subgroups. You can forget about subrings and about expanders and all these things. We're interested in approximate subgroups, and the question is, where do they come from? You know, previously we saw it seemed to be a combinatorial definition about some finite sets, but we'll see that to classify them, you need some other mathematical objects. So I repeated the definition. Okay, I think I already said this. So I want to give you a class of approximate subgroups, which are not equivalent to groups. And for that, I'm going to talk about Lie groups. So let me just introduce that for a minute. So for the purposes of this talk, you can certainly think just of groups of matrices. If you have a group of matrices with real values or with complex values, let's say SLN of R, it means all the matrices, n by n matrices that have determinant 1 with real coefficients. And this group is also, it has a topology, which is induced by the reals. It has a differentiable structure, and it carries a measure, which is forget that. It does not necessarily carry an invariant measure. But anyway, you can just think of a closed group of matrices with complex coefficients. And there's tons of beautiful mathematics about it from the 19th century and the 20th century. So for example, the simple Lie groups, you can just write down a list, essentially. You can also widely generalize this class. For example, these are all locally compact. The reals have the property that every, so locally compact. You have the basis of compact neighborhoods of the identity. So this is a very, very general class. Here I wrote a very specific class, but there's a lot of mathematics saying that the difference is not as big as you would think. But locally compact groups, let's say connected locally compact groups, are built out of Lie groups. Anyway, here's a simple lemma. Maybe you've had a chance to, have you had a chance already to read it? Yes? Should I skip it? But this says that we have many interesting examples of approximate subgroups. Namely, take a compact set which includes the identity inside it. Or make it symmetric if you want to consider symmetric set. Okay, any compact set. Well, yeah. Yeah, so what happens if you multiply it by itself? You get another compact set, right? If you take a compact set, x, and you apply a continuous function to x times x, you're going to get another compact set. So is it commensurable to the original set? Well, in fact, all compact neighborhoods of the identity are commensurable to each other. And the proof is very simple. It's just an application of compactness, right? So one of the sets can be covered by some number of translates of the other, and therefore by finitely many translates, right? Okay, so this is a source of approximate subgroups. And if the group is not compact, if the group is, I'm not, the Lie groups are, some Lie groups are compact, but I'm not interested in it. So if the Lie group is not compact, for example, like the SL2 of R, it's not compact, then you get an approximate subgroup, which is not, there's no subgroup nearby. Yeah. Now, if you have Lie groups, if you have a certain class of approximate subgroups, you can always pull them back to other groups. So if you have a homomorphism into a Lie group, and you pull back one of these compact neighbors of the identity, then if you think about it for a minute, the inverse image will also be an approximate subgroup. So one way to get an approximate subgroup of G is to take a homomorphism from G into a Lie group, a kind of representation of G. Okay. So for some reason, which will not come up in this talk, approximate subgroups obtained in this way will be called laminar. Because of some kind of something which looks like turbulence, which happens in the other one, but that doesn't matter. Okay, so this example I gave before. And I'm just pointing out, where's the locally compact thing around this example? Well, you have the reals themselves. And the reals have an approximate subgroup, the interval from -1 to 1, for example, right? So if you pull it back under the function that maps x to x over n, it's a function that fills out somehow a denser and denser subset part of the reals as n becomes big. Then you just get the Feynman, the obvious approximate subgroups.
Question?
Yeah.
Is there an interpretation for approximate subgroups in terms of fundamental groups and covering space theory?
So the first implicit occurrence of approximate subgroups was in Goldman's paper on groups of polynomial growth. Because if you think that means that you have a set X such that when you take more and more and more, a finite set such that when you take higher and higher and higher powers, the growth is only polynomial. But if you think about it, that means that very frequently these sets, which are n-fold products of generators, is very frequently going to be an approximate subgroup. So it actually fits in our setting. And yeah, I mean, he was inspired by work on the fundamental groups of certain manifolds. Yeah, so there are connections. Okay, so here's the first theorem that, remember, amenable meant that there was an invariant measure around. And if there is an invariant measure around, then the group is laminar. In other words, in that case, the explanation of what these things are afforded by Lie groups is a complete explanation. Originally, I assumed amenable in a certain strong sense that it's definable, and later this assumption was removed by Masiko and Wagner. Right. So this was very natural to prove. This was very natural thought given some knowledge of some model theory. And I will not be able to describe in detail this connection, but I would like to at least give a hint, an indication of why it becomes natural if you know some model theory. So I'm continuing, so I'm switching to the other line and talking a bit about Galois theory. Yeah, and okay. Although I will not be able to get to a hermetic contact between them. Okay, so the algebraic closure is interesting in itself, but also it's very important if you, even if you want to know higher dimensional things. A lot depends on the algebraic closure. So, for example, you might be interested in irreducible varieties in algebraic geometry. So they are cut out by, let's say, one polynomial, but with many variables or more than one variable. Okay? And you'd like to work with irreducible ones because that means that there's some notion of generic behavior that that you can, if you ignore smaller dimensional exceptions, then all points somehow look the same, they have the same behavior. But this will only be true in irreducible varieties. It will not be true in a union of two varieties. There will be two generic behaviors. So if you take a set like x squared plus y squared equals 0, and remember we're thinking about complex solutions, not about rational solutions. Anyway, it's irreducible if you just, this polynomial in Q of x is irreducible. You cannot factor it. But nevertheless, there isn't, although V is irreducible, if you're interested in pairs of elements, you look at V times V, it's not irreducible anymore, right? Because over the complex numbers, it's a union of two lines, X is either IY or minus IY. And if you look at pairs, then, well, the pair could be both coming from the X plus IY or both from the X minus IY. Maybe that looks the same because I and minus I are kind of the same. But they might be coming from both on the same side or from different sides. So, okay. So somehow, if you work over the algebraic closure, if you allow yourself to factorize not only by rational numbers, but also by algebraic numbers, then irreducibility behaves better, and there's a better notion, a better behaved notion of the way that a pair of elements can look, if you know how each one can look. A pair of elements or pair of elements of a variety. So this was generalized by Shelach to arbitrary stable theories. I don't want to get here into the definition of stable, but to a wide class of theories, which we'll need to extend more and more. And anyway, he proved that there's a canonical amalgamation over the algebraic closure. It will not be true without, and this also requires working with imaginary lines. So, we're going to want to come out, when you have an approximate subgroup, you look for, first thing you do is you look for groups nearby. And so if you have some set V and your generic means you're willing to throw out lower dimensional things, you can look at the stabilizer of that V. Namely, you can look at the elements A such that for a generic X in V, A times X is still in V. So if you have such an element and you have another one which looks the same, satisfies the same formulas, the statement is that the product has exactly the same property. So now we've got an actual group, some behavior such that if A has it and B has it, then A times B has it. Okay. So when you begin to work with approximate subgroups, if it's in a stable setting, then you can do it. So if you just try to prove naively that if A is in the stabilizer and B is in the stabilizer, then A times B is, it will not be work immediately before you realize something like this, that you have uniqueness of two amalgamation. That if you understand how A looks and how X looks, then you understand it here. So this was for stable theories. people wanted to go further to a class called simple theories, and there you don't have canonical two amalgamation anymore. But there's a substitute, which is three amalgamation, namely, is there a pen? Okay, it doesn't matter. Oh, thanks. Yeah. So before I talked about understanding the behavior of two elements. If you understand what happens to each one, and are willing to throw out small things. And three amalgamation is different. That you have three elements, and you assume you understand the two types. You understand each pair. Then the question is, can you fill it in and find a triple which has the given behavior of each pair of variables? And it turned out that first of all, in a wider class of theories, you have three amalgamation. It follows from this unit two amalgamation, but you have it in a wider class of theories, and that if you have it, then the stabilizer, it's a bit more surprising maybe, but the stabilizer still works and gives you a group. So if I have time, which I doubt, I will discuss it more towards the end. However, what is the price in this? Okay, so okay, I will get to it later, I hope. But anyway, the price for this was that the Galois group is no longer profinite. It's still a compact group, but it may have connected components, and the equivalent, the imaginary elements you need to look at in order to make this true are no longer definable. You get equivalence relations which are defined by infinitely many formulas, by the conjunction of infinitely many formulas. These, when you factor them out, give you not necessarily finite sets anymore, but compact sets. And if you start with a group and you factor out a subgroup, which is defined in this way, it has bounded index in some way. It's defined by an intersection of definable subsets, which comes out to be a group. And such that each of these definable subsets, in some sense, has finite index, then the whole thing, the quotient of it, is a compact group, no longer a profinite group. And this connection is really the same connection that allows us to pass from approximate subgroups to Lie groups. So I'm skipping over the passage from compact to locally compact. You have to generalize in some way when you do this. Okay, so that's nice. So we now understand the source of approximate subgroups which are amenable. But what if they are not amenable? So already for groups, many groups are not amenable. If you take SL2R, there's no translation invariant measure on it. So what about the other ones? So here's another family of another class of mathematical objects, another way to get approximate subgroups. And this is about quasimorphisms. So now it's not the group which is approximate, it's the morphism. So here's it's a subject which I didn't know anything about it before I started working on this, but it's a very rich subject, and quasimorphisms are very, very well understood. What is a quasimorphism? It's a function from the group into the reals, specifically into the reals, such that, well, it's approximately homomorphism in the following sense that f of x times y is not equal to f of x plus f of y, but the error is bounded. And you can set it to 1, or you can just keep it bounded. Okay. And there's a trick. Okay, and these, if you add to it a bounded function, of course, it's still going to have this property. So we're not interested in, we don't care about changes by bounded functions. And there's a way to normalize and to get yeah. So in any class up to bounded functions, you can get a quasimorphism which at least respects powers exactly. And that's a bit more canonical. Okay. So okay, so that's definition, but there are many of these and they're very, very well understood. And I gave here a side remark. Yeah, so this notion of approximate homomorphism is about, is defined in this way, but you have another famous notion in quantum mechanics that you consider maps which are additive, but only on commuting variables, not on non-commutative ones. So this, to explain it exactly, you have to pass to the Lie algebra. Let's say of the unitary group, which is some kind of self-adjoint operators, and people have been interested in studying quasi-states in which f of x plus 1, so if x and y are self-adjoint operators, then f of x plus y would be in that case equals f of x plus f of y, but only when the operators x and y commute, not in general. Right? So there's a famous great theorem of Gleason saying that quasi-states are actually states. But if you know that they commute on commuting things, then basically they commute. And this was pointed out, this connection to quasimorphism was pointed out by Protorovich, and they also pointed out, and Entov, and they also showed that in the symplectic group it's different. You do get very interesting quasimorphisms which don't come from homomorphism. Anyway, oh, yeah, so here's an example. You take the automorphisms of just the ordered set of reals, but also the function that takes x to x plus 1. So basically, if you take any order preserving map, for example, from 0, 1 to itself, you can always extend it to an automorphism of this thing. And this is very elementary to try to play with it if you like. If you map such a G to G of 0, that's a quasimorphism. It's not a homomorphism, but it's a quasimorphism. Right, and finally the connection to approximate subgroups. If you have such a quasimorphism, you can try to talk about the approximate kernel. It means the inverse image of some bounded set. And all of these are approximate subgroups, commensurable to each other. And again, it's something that you can do as an exercise. I didn't do it all the way. Yeah, so if you choose R big enough, I tried to compute what kind of approximate subgroup it is. I got 5 approximate. So x times x is a union of 5 translates of x. But maybe it's better. I don't know if it's optimal. Okay. So this is the second abstract theorem about approximate subgroups. So these two sources are enough. There's a way to put them together, which can be described in multiple ways. But one way is the following. You start with a homomorphism into a Lie group, as before. You have the kernel. It's some kind of group, which can be, some kind of group, subgroup of G. And then you take finitely many continuous quasimorphisms into the real numbers, and you look at the intersection of these finitely many approximate kernels. So this gives an infinitely definable object, because here it was infinitely definable. The kernel of rho is the intersection of infinitely many formulas, and therefore this is infinitely definable as well. It means that they're approximated canonically by a family of definable things, and these are each, that makes a commensurability class of approximate subgroups. So now the second theorem, which does not assume amenability anymore, is that in these two ways, you obtain all approximate subgroups.
I have a question. Why does it remain type definable after applying the reimage of the continuous functions?
So I mean, so continuous in the sense of continuous logic.
Okay.
So yeah.
That's fine.
Okay. Yeah, I didn't go into the details of the topology, but many people know. Okay, so this was a bit abstract, and now I'd like to mention two corollaries in increasing degrees of concreteness. And for this, I need to talk about the subject of lattices and approximate lattices. Okay. So, yeah, so before we talked about finite volume, now we're going to talk about cofinite volume. So when you have the integers inside the reals, for example, if you factor it out, then you get a circle which is compact, and it has finite volume, right? So you say that the integers in the reals are co-compact. And in particular, they have co-finite volume. There's a finite volume set, some pi from 0 to 1, let's say, such that if you add it to the group, then it becomes everything. Okay. So there's a notion of co-finite volume, and a lattice is a subgroup, a discrete subgroup of finite volume. So for example, SL2 of Z, the 2 by 2 matrices of determinant one and integer coefficients, it's obviously discrete in SL2 of R, but in fact, and it's not co-compact, but it is a lattice. So this is very famous from elliptic curves and various other connections. It comes up. It's non-trivial, by the way, but it's true. Right, so this is a lattice, and they're very important, both commutative and non-commutative ones. And an approximate lattice, same definition, is a discrete approximate subgroup, okay, which has finite co-volume. Now it's not easy to define what is the co-volume of an approximate lattice, but the fact that it's finite is well defined. It doesn't depend on it. So yeah, there's a complementary thing of finite volume. Okay, so these were introduced for reasons of number theory. So there was a book by Eden Yale, which I forget the title of, but something like harmonic analysis and number theory, something like this, where he introduced them. Oh, I see this slide is just giving credit to people, so you can read it quickly. But yeah, Björklund and Hartwig tried to do the non-commutative generalization. Machado did a lot of work, some of it in parallel, and some making completely clarifying the subject later. And I'm mentioning another path to actually, it's in the wrong place. It's another path to the previous theorem by different methods using topological dynamics. Still using model theory to give you the models that I mentioned before that have lots of automorphisms, but after that using some tools of topological dynamics. Okay, so here's a picture of a lattice. So they come from chemistry. So I got this picture of salt. So everybody knows, right? So you have R3, and inside it you have Z3 somehow. But the way this Z3 fits the Euclidean metric can change. And these different ways were completely classified in the 19th century. This is a cubic lattice. And I don't have much time, so this is, I'll just very quickly say that, okay, R3 is in a regular way tiled by the cube, right? But there was a question of whether there are also ways of tiling, kind of special kinds of molecules, if you like, that do tile the plane of space, but only in a non-periodic way. Okay, these are called aperiodic tiling. Of course, these would be, so the first proof that there exist aperiodic sets of dominoes like that in the plane was done by logic, but I'm going to skip it, by Wang. I'm going to skip this proof. Yeah, but then after Wang proved it in an existence theorem, a number of people found concrete finite sets of tiles which do tile the plane, but only non-periodically. And this is the most famous one, the Penrose tiling. There was also one with a few more, but still not that many tiles. Raphael Robinson, a little before that. And then physicists started looking at it, and they said, well, can we actually make such a molecule? Because it will lead to materials which are not crystals. They don't come from lattices, but still they have some so-called aperiodic order. And here's a picture of one, which was actually found in, it was first found in somehow artificially constructed materials, but later it was found in nature. Although apparently they arise only in very violent events, like a meteor crash. Yeah, so this is a picture of what, what mathematically is supposed to correspond to the Fourier transform of a set in the plane, which has a Dirac measure. It has measure, but only on a discrete set. And you can do that by electron diffraction, and you see something which is still discrete. And it's not something you would expect. Usually you would expect just to see a mess, but you see something which is still discrete. This happens for lattices. If you have a lattice and you take the Fourier transform, then you get another lattice. But it doesn't happen for very many other things. And in fact, the answer to what it must be was given before all this physical stuff by Yves Meyer. Yeah, who proved that if you see this thing, if you see a diffraction image which is discrete, then it must be that you started with an approximate subgroup, in fact, an approximate lattice in Rn. So he, so he explained all the approximate lattices in Rn, and there's something interesting here. So before it was just an aside, but here's something quite interesting. They all come from lattices. So all approximate lattices come from lattices, but in higher dimension. So this was a phenomenon which was studied earlier by Howard Ball with functions, but here it's studied with sets. You do the following thing. You take a lattice in Rn times Rn, okay? You intersect it with a strip on one of these. So the Rm, in this case, you restrict it to something compact. And then you project it to the Rn. So it's not very difficult to show that if you do that, you may not get anything periodic anymore, but you will get something which is quasi-periodic. You will get an approximate lattice. And Meyer proved that's the only way. I have a picture. Here it is. Yeah, I didn't do it with it. It's not a very good picture, but the point is that the lattice should be. You really should look at it from the way I'm looking at it now, so that you think this is the direction of x to the n, and the lattice is at some irrational angle to the direction of projection. So then, inside this strip, you're later going to project it just to this line. It will be true that if you go 2 steps, you will definitely encounter a point, but it will not be at exactly regular intervals. There's an irrational number. Okay. Now, Bjorklund and Hartwig, they did a lot of work, and they asked whether this classification of approximate subgroups holds for approximate lattices, also in the non-commutative case. Let's say for n by n matrices. And if you think about it, the definition doesn't require commutativity. It just says, here's our G, and we started with a lattice in G times H. There's some secret dimensions which we don't see in this H. And we do the same thing. We intersect with a strip, and we project back to G. You always get an approximate lattice. This way it doesn't need to be commutative. The question was, are they the only one? And yeah, and the answer is yes. For a wide class of groups, which includes, let's say, SLN of R, SLN of QP, this is true. And I wrote some proof of some this is just a proof that sets constructed in this way are always approximate lattices. Skip. How much time do I have? 5 minutes?
Well,
but I started like 12:15. You know?
sure.
What? 10 minutes? Okay. No, I'm doing okay. Maybe you'll fine. Yeah. Okay. So I just stated that theorem. And in fact, you can go further a bit. Yeah, so there's a complicated definition of arithmetic lattices, which is very important. Number theory, in automorphic forms and things like that. And I'll just give a definition by example. I'm not going to give a definition. But SL2Z, I said by non-trivial theorem, it's a lattice. And it's an example of an arithmetic lattice for obvious reasons. Now there's something nice. Boyle and Harris-Chandra proved that if you take SL2 of Z of 1/3, you allow denominators with only the powers of 3. Well, take that one. It's also an arithmetic object. If you view it as sitting in SL2R, it sits in SL2R, of course, but it's dense. It sits also in SL2 of Q3, but it's dense. But however, if you take both projections, you view it as a subset of the product, it becomes a lattice. This is an arithmetic lattice. And yeah, so again, if you want to look, now if you want just lattices in SL2R, you don't want this product, you can do the following thing, same thing, cut and project. You take SL2 of Z3, so it's a lattice here, you take a strip with a compact subset here, you intersect and you project. And this is the source of all this kind of thing, how you get arithmetic lattices. Now, yeah, but look, there's an asymmetry. In order to get an approximate group, not an approximate, in order to get a group, which might be a lattice, I had to intersect here with a compact neighborhood of the identity, which is a group. Okay. This exists for Q3 because you have Z3. So that's okay. But if you say, well, these should be symmetric, they're both two completions of the rationals, they're supposed to have equal rights, they don't. Because SL2R doesn't have any subgroups which are compact to it. However, and this was a really nice observation of Bjorklund of this paper, don't take a subgroup, just take any compact neighborhood on the R side, project to the Q side, to the Q3 side, you do get an approximate lattice. So by generalizing to approximate lattices, we somehow smooth out the theory of arithmetic group. And here's a theorem that, yeah, basically approximate subgroups lattices in SL2 of these, let's say in SL2 of R, they're all arithmetic. Yeah. So the last thing I want to say is to make that more concrete, so that because the first theorem was very abstract, and you might think maybe it's just playing with words, but I don't know how to directly find approximate lattices in SLN, but using these theorems you can. And I want to describe what it looks like even for SL2 of R. So I need the notion, just as you see, it's very arithmetic, you need the notion of a Poisson number. A Poisson number is an algebraic integer, which is most likely not rational, but somehow when you take powers off it, they come very, very close to integers. So this is Poisson numbers. So for example, if you look at Q the square root of 2, they're going to have the form a plus b the square root of 2, where a, b are integers, but such integers that a divided by p becomes close to the square root of 2. So I mean, the integers you get by rational approximation. Okay? In this case, it's very easy to see. You see, if you take a plus b square root of 2 plus the conjugate a minus b square root of 2, that is an integer. You take the sum of the two conjugates. And this factor that we added to it is obviously exponentially small when n becomes b. Right? So the original number, a plus b square root of 2, is a Poisson number. And these are very special. They have a place in many things. And here's the theorem, is a totally concrete description of lattices in SL2R. So first you need a number field. within that, and now we're taking the matrices, which are close to the identity, but in a funny set of clothes, namely, you get that the entries are Poisson numbers. This is an approximate lattice. So this family of approximate lattices corresponds exactly to number fields. And they're not lattices if the number field is not Q. And then there are similar quaternionic things, and the theorem is that all of these are all the approximate lattices. So these proofs are not all, they require many things. So I mentioned earlier the work by Gleason and Yamabe and Montgomery Tsipin in the 50s about classifying locally compact groups. So the model theory just gives you an entryway by finding some locally compact group, and then it was used. And here, likewise, the model theory somehow brings it to the right place, and then you use deep theorems of Morgulis. It doesn't go by itself, but some of the transition is done by model theory. Okay, so now it's going to, I don't know, should I stop or
maybe
people are hungry?
yeah, just wrap up because really this.
Yeah,
I think this is
okay. No, I can wrap up here. This slide is only to say I described a bit the model theoretic, the progression of this search for the model theoretic Galois group, and I already mentioned it up to about here. And okay, still in the previous application, yeah, I even mentioned the three amalgamation suffices. And compact groups. Now, the next step, actually, historically in time, it was displaced. Lascar was earlier, but anyway, he was interested in finding the right analog for the Galois group, and he looked at the maximal quotient of M of the automorphism group of a saturated model, which does not depend on the actual choice of the model, which depends only on the theory. And he found a group which was very mysterious because it had you could not give a good topology to it, and it was not clear if it comes from the automorphisms of some structure. Anyway, but it turned out that this group is exactly the obstruction to a kind of three amalgamation. To a three amalgamation when two of the sides you want them to be equal. Yeah, then there was, so it was a very mysterious group. It helped to show that it's you can view it as a compact group, modulo a closed subset, meaning modulo the group generated by a closed subset. So that's a dense subgroup usually, which you don't want to mod out by, but it's what you need to do to get the Lascar group. And there's a construction, a canonical, this can be done in many ways, but there's a canonical way to do it, where it does come with a canonical geometry which is being acted on, and this leads quickly to the structure theorem that I mentioned for arbitrary approximates. Okay. Yeah. Okay, so I'll stop there.
questions?
You take the real numbers, you fix one of these Poisson numbers, and you add a predicate for its powers. You expect something untamed because it's close to the integers, or it's far enough, so, for example, dependent or something. So that's a monotheoretic twist. A way of understanding these powers is add a predicate for the collection of powers of the Poisson numbers, add it to the reals, and look at that structure.
I see. That's a great question. I know. I don't know. Yeah, it's a very good question.
Another question, please.
I'm curious, even if it was not the main theme of the talk, you mentioned that there was this theory using recursion theory that there are non-periodic tilings. Can you say a little bit more about that?
There do exist tilings that are only non-periodic. Yeah.
Yeah.
Yeah, I even have a slide on it, I think. But it's a very simple thought that if it were true suppose it were true that any finite set of tilings which tiles the plane at all also tiles it periodically. Yeah. Then the question of whether something can tile the plane, you give yourself some set of dominoes, you ask maybe with colors, you ask can it tile the plane? That would be decidable. You have an algorithm to decide it. Because if it tiles the plane at all, it tiles it periodically, and it's kind of easy to search for periodic tilings. On the other, this is on the one hand. On the other hand, Wang showed that you can code a Turing machine by the question of whether a given set of tiles tiles the plane. And it's also not too surprising. There's one mathematical thing that needs to be done, but it's not too surprising because you can think of the tiling of the plane as the total space, some of the run of the Turing machine, which so you think of one dimension as being the state of the Turing machine, the other dimension being time. So at a given point, you have some symbol for finitely many symbols, and you can try to, the rules for when the dominoes can be next to each other and tell you if you're on a Turing machine. So it's undecidable. So you cannot tell if something tiles or not. There's no algorithm. So the only way out is that there must be tilings which are not periodic.
I don't have a question. It's more like a summary question because you promised, I mean, there are two areas and you said a lot of really interesting things on approximate subgroups, lattices in particular, that seem to connect with many things. And then also there is a search for the monotheoretic Galois group or object or something. That final link was very quick. Can you just summarize in a short sentence what would be at the moment the connection between those two, just as a summary? Maybe you said before.
So there were two. Basically, there were two theorems. One about amenable approximate subgroups, and one about arbitrary approximate subgroups. And the rest of the work, once you have these structure theorems, the rest of the work is mostly group theoretic. You need to rule out. Okay, anyway. So you have these two theorems, and I guess I try to at least suggest how. So for example, you just given an approximate subgroup abstractly. It's not that obvious that there's in fact canonical Lie group associated to it, right? So I try to suggest how the development of model theory did make that a natural thought, and in fact helped with the proof also by asking which aspects. So first of all, the fact that one can define the stabilizer in simple theories. Here we don't have a simple theory, but somehow having a measure around is very similar. And secondly, in the fact that you have, so it comes from the amalgamation, but the amalgamation, it can only be true over an algebraically closed set, and the notion of algebraically closed had to be changed in continuous logic in order to get compact groups. So this was one. Yeah. And for the second theorem, I said it a bit more sketchily, but what happens is that I don't know where it is exactly. Yeah. Okay. When you want to understand the Lescar group as part of a group that actually acts on something, you have to construct this something. And the something that I use is something called, it's a certain structure, which is like a type space, but it's not just a set, it's not just a topological space, it has some structure on it. Okay. And because of that, it's related to the actual models of the theory. Canonical is a canonical object, therefore you would expect, but it's canonical not after unique isomorphism. So therefore, you would expect maybe the automorphism group of the model to act on it, but it actually only quasi-acts on it. It acts on it up to the notion of a Lescar neighbor, up to this kinds of isosceles pre-amalgamation. So that's where you see the approximate. You get a theorem in which, because this Laskar relation is totally canonical, it's not random, yeah, the error set that you get in your, you get some kind of quasi homomorphism, and the error set is a normal set. And this is a very, very powerful property that allows you group theoretically to proceed and structure.
Yeah, well,
Thanks for the question. Yeah.
okay. Yes.
Well, I have a vague question, but since you mentioned Piso, and for me, Piso is substitution and Piso conjecture and tilings. I don't know if you know about this.
Maybe I think I probably heard one, but I don't remember. What is the
So the point is, if you have a substitution, you can take the realization of the substitution, and then you get a matrix. And so when the matrix has eigenvalues, and I mean, since if you take the substitution is reducible, then the matrix is negative, so power is positive, and you have Rotovenus. So the leading eigenvalue, if that is Piso, that the conjecture is then the dynamical system would be not weak mixed with a pure point flat spectrum. But it also can be formulated in terms of timings, because I mean, from timings you get substitutions and the other way around. And so, I mean, I said it was a big question, but I mean, you mentioned Piso, you mentioned timings, and you mentioned this. So my question is, I know, have you heard about this? You can,
no,
you can
so in fact, I haven't.
okay.
I haven't. I'll be happy to look.
Yeah, because I mean, that's a very big problem.
It sounds like it's in part of the same world.
Yeah, exactly. So it's kind of along all the line. I mean, I said nothing about the theory, but I mean, it seems like it's really next to a lot of important.
Yeah, thanks very much for pointing this out.
Dynamics.
Right. Yeah, I'll look it up.
Well, if there are no further questions, let's thank Louis again. Buen encuentro. Oh,
I'm not sure. Someone knows how to pronounce it.
Sorry, I mean, I'm not expert in that either, but it's just like, there was a lot of things like, I don't do some dynamics, but I sometimes work like instructions. I mean, there was a lot of words that come out in your talk, but also come there, so I was guessing maybe you can say something. No, I know. It was